So let's get started. It's a real pleasure to be here. And so my name is Arman Ramim. I'm a medical physicist, a professor of radiology, physics, and also biomedical engineering here at UBC, and also at the BC Cancer Research Institute, which is a research arm of the BC Cancer Agency. First of all, I really acknowledge Dr. Stuart Jackson, who used to cover these lectures years ago, and he was graciously sharing the lecture notes with me, and we've built on top of that. So some recommended or texts that you could consider. Here's one example, the so-called Cherry textbook, which is a really classic, reliable text to go to. Here's one by Saha. What I like about this one is that it does emphasize radiobiology quite a lot towards the end of the text, so which we're not covering at all. And I believe you will have some lectures on that, but by others. But radiobiology is covered well in this book. And here's a book that I had the pleasure of co-authoring myself with Dr. Ramesh Chandra. This is the 8th edition here. And this one is more introductory than, for example, the Cherry text. So to really get into the field, and it's more condensed. So you could potentially read it cover to cover, or a good amount of it, because it's half the size basically, and it's more introductory. We do have me and my colleague, Dr. Carlos Uribe, we have a YouTube channel where we have over almost 50 videos because of the course that we were delivering. So that's I think about over 30 hours of lectures on nuclear medicine, but of course I'm condensing this content down to about 5 to 6 hours for you, for our great residents here. So you may want to check that out. You could just search on YouTube for Curate Education and Research, and you can look that up, and here's a link also. So the outline of what I'm going to be covering in these 5 to 6 hours is going to be an introduction to nuclear medicine, and please feel free to stop me anytime. Looking at how imaging is done in nuclear medicine, what is a gamma camera, quality assurance aspects, what is tomography, how do we do tomography, especially in nuclear medicine that leads to SPECT and PET imaging, how do you do reconstruction, and some of these you'll see overlap with what you might have learned so far on CT, for example. Some of the concepts, some of the core concepts, but of course they're very different in some other sense, because in our field we were dealing with emission, whereas an emission tomography, whereas in CT imaging, you're dealing with transmission tomography because the source is outside the body, whereas in nuclear medicine, the source of radiation is inside the body. So SPECT imaging, PET, and finally, the very exciting and emerging or re-emerging field of nuclear medicine therapy, also known as radiopharmaceutical or radionuclide therapy. So nuclear medicine, basically, what is it? And we're dealing with radiopharmaceuticals that are used to image the structure, and especially, what's the valuable point is the molecular and the functional aspects of the body, of organs and biological processes. They're sometimes called radiotracers, because they're injected in tracer in small amounts, but this is for imaging. In therapy, you shouldn't be calling them radiotracers because you're not supposed to be injecting small tracer amounts. You're supposed to be injecting large amounts. And if they're really concentrating well in specific locations or in certain, for example, tumors or cancer cells that express certain proteins that you're binding to, then you really do want to be injecting a lot. And so in that case, we just call them radiopharmaceuticals, for example, because you want it to sit there instead of imaging, you want it to bombard the tumor, for example, with high doses. So both sides are very active, imaging and therapy. And therapy in the past, half a decade is just undergoing tremendous growth. A lot of exciting results, which I'll be talking about. So radiopharmaceuticals are designed to mimic a natural physiological process. So they're tagged with a radionuclide that emits gamma rays and produces images of function as opposed to anatomy. And so this could give you a single image, or it could give you dynamic images. For example, you could get a dynamic image of a certain organ and track how the uptake in the organ, for example, changes over time. So this would be dynamic imaging. So what would be an ideal property of a radiopharmaceutical? Ideally, you would like it to have these energies between maybe 100 to 300 kilo electron volts, because if it's below this, then it's scattering in the body left and right, and it's not making its way to the detectors. Whereas if it's more and more energetic, then it becomes more and more difficult to capture it, and you have to build thicker and thicker crystal, giving you more and more expensive scanners, and therefore the sensitivity would come down. You'd like it to have a relatively short half-life. You don't want it to be too short, because then transportation becomes difficult. You know, figuring out by the time it's produced, till the time you inject into the body is going to take a while. You don't want it to be too long either, because you're injecting into the body. If it sits there forever, then you cannot inject too much, and therefore you're not going to get high quality images. You don't want it to emit particles. You don't want it to have particulate emissions, because if it emits particles, the particles are going to be actually harming the body. Except, again, if intentionally you're using radiopharmaceuticals for therapy. So in that case, you definitely do want them to have particulate emissions. You want them to rapidly localize. You don't want them to be toxic. So for imaging radiopharmaceuticals, technetium really fulfills this. Technetium, we'll see in a bit, it has a 6-hour half-life and an energy of 140 kilo electron volts. We'll see that in a bit. So radiopharmaceuticals localize in the body using different phenomena mechanisms. Active transport is one of them. Diffusion, phagocytosis is one. Cell sequestration, we're going to see an example of this, where you used to do splint scanning with damaged red blood cells. You damage red blood cells, inject them into the body, and because the spleen is supposed to deal with that, it accumulates in the spleen. It's kind of a very cool phenomenon. Just showing the amazing range of things you could do in nuclear medicine imaging. Phosphorylation, so along the glycolysis pathway, like here we have fluorodeoxyglucose. You can sort of think of it as radiolabeled sugar, sort of, right? And in that phenomena, you could be imaging the body's metabolism, which is what we do in PET imaging using fluorodeoxyglucose, very, very commonly used. Receptor binding is very, very popular these days. Neuroendocrine tumors, for example, and antibody-antigen binding is also another phenomenon. So the promised example of spleen scanning. So if you heat damage some red cells and then inject them into the body, well, the spleen's normal function is to remove damaged red cells, right? So you start seeing like accumulation in the spleen. So that's a very cool idea that used to be used to image the function of the spleen. Just showing you that the sky is the limit in terms of the kind of things you could do in nuclear medicine imaging. Technetium again. So you start with the parent isotope, right? So the parent in this case would be molybdenum-99. It emits into technetium 99M, which you can think of it as like an elevated state of technetium-99. And then it emits to technetium-99, and that phenomena, that transition, takes about the half-life is 6 hours, and the energy is 140 kilo electron volts. So it's kind of ideal. Now, how are these radionuclides actually produced? Without going into too much detail, just remember there's really 3 ways that are used. One is to use fission products. You've heard of fission. From the few rods of a reactor. So you have a large molecule and somehow you break it down. That's what fission is. You break it down into 2 smaller molecules, and so this or isotopes. So in this case, you're having uranium being broken down into molybdenum-99. There's another way to produce the exact same thing. In that case, you start with something else, like molybdenum-98, and you add neutrons to it. And that's what nuclear reactors are, because in nuclear reactors, you are, through whatever phenomena that you're doing, you're producing more and more and more neutrons. So you have lots of neutrons that can be used to attack other radionuclides, and those then can produce other radionuclides. So this is called, another phenomena where through which molybdenum-99 is produced. Interestingly, you might have heard of cobalt-60 in external beam radiation therapy. Before LINACs and linear accelerators, which are the norm these days, people used to use cobalt-60. Even right now in Vancouver, we have one example that I know of where instead of LINACs, they're using cobalt-60. So how's cobalt-60 produced? Well, you take cobalt-59, you add a neutron to it, and then you get cobalt-60, which has a very long half-life of 5 years. Obviously, you can't, you cannot inject that into patients. This is for external beam radiotherapy. But molybdenum-99 in this example has a half-life of around 66 hours. And finally, you can use cyclotrons, which are much more affordable devices than nuclear reactors. So you're adding protons, right, or deuterons, which are positively charged particles. You're adding them to something, in this case thallium, to produce something else. So finally you end up with this kind of a thing. Like you start with something else, is one kind of an isotope of thallium, and you finally end up with this kind of thallium, which is actually used in cardiac imaging in SPECT. So molybdenum-99 is this parent, right, that we saw. One example was when you break down uranium-235 into molybdenum-99, and then you ship it to places, and then you get technetium-99m, and you need to separate these two from each other. There's a half-life of 6 hours, so transportation can be done relatively easily. So how do you actually then separate these two from each other? It's like the parent and the daughter are together. How do you separate the daughter, which is technetium-99m, which is what you want to inject into patients? How do you separate that from the parent? Well, to do that, you use generators. So let me show you an example of that. Oh, actually, before I show you an example of that, I want to emphasize to you that molybdenum-99m can also be produced using other means, not just using nuclear reactors, but using cyclotrons, which is a sort of a very interesting invention that was, for example, really promoted and done in Canada. Here are examples of fantastic colleagues here at BC Cancer Agency, Dr. Benard, Dr. Schaefer, and Dr. Ruth, who were kind of involved in this amazing project. So because of shortage of sources available using nuclear reactors, for example, because there's only a few centers in the world, sometimes there's shortage as well. Guess what? Cyclotrons are much, much smaller. Every center can have its own, or many centers can have their own cyclotrons to produce this. So this is some innovation that continues to be work in progress and in discussion. Should one be using the conventional ways, or should one be switching to cyclotrons? So technetium generator, pretty much think of, okay, so you have these things, these materials, the alumina, acid alumina, right? Aluminum oxide, basically. And they're porous and they're highly absorbing. So you load the molybdenum, which has created an ion, highly charged ion with 2 negative charges in here, and it just cannot pass through. Whereas the daughter that is created from this is technetium, which in an ionic form becomes pertechnetate, but it only has a -1 charge, not -2 charge, and it more easily passes through here. Especially if when you do sailing, you basically pour saline, and so basically the daughter is able to pass through here, but the parent gets trapped. Just kind of tragic, I guess, right? The daughter makes it. So the daughter makes it, and you care about the daughter, not the parent in this example, right? So you want technetium-99m to be separated from molybdenum-99. You definitely don't want to be injecting this into patients because it's got a long half-life, whereas this is a short half-life, 6 hours, and there you have it. Now there are many different isotopes. There are in fact over 1,000 radioisotopes that are out there. Well, a fraction of those can be used in existing scanners and devices, but there's actually a lot of them that can be used. Like here's an example: technetium, thallium, gallium, right? So you make your way down here. And these emit either gamma rays, so single photon. So this allows you to do planar or SPECT imaging, or they emit positrons. And as you'll see in later parts of the lecture, positrons can combine with electrons, and they produce 2 gamma rays going in opposite directions, 2 photons, not 1 photon. That allows you to do PET imaging. So anytime you see gamma rays, is for SPECT or single photon planar imaging or planar imaging. So single photon can give you either planar imaging or SPECT tomographic imaging, or you could do positron emission, and that gives you 2 photons, and that allows you to do PET imaging, as we'll see later. So many different things that you could do. Often these are injected into patients, but here's a counter example to that, where we've got technigas just as an example. This could be technetium labeled, or it could be also inert gases like xenon or krypton that are injected into the patient, that are actually inhaled, right? And so that can be used for ventilation studies, to study the flow of air in the body. And you often inject that with a pair, radio tracer. In this case, for example, MAA is mentioned to study flow of blood. So you're studying both flow of air, that's ventilation, and flow of blood, that's perfusion. So that gives you a ventilation perfusion exam, which is very valuable, as you know. For example, used to diagnose pulmonary embolism. Here's an example of some radiopharmaceuticals in PET, the ones that emit positrons. And so examples are carbon, nitrogen, oxygen, and fluorine. And these are labeling certain molecules, because these molecules end up measuring a certain physiological process. So many, many different things can be measured. You could measure hypoxia, you could measure perfusion, you could look at the receptor binding in the brain, et cetera, et cetera, et cetera. Many different applications, oncology, brain imaging, all kinds of different applications, actually, neurology, cardiology, et cetera. So sky's the limit, actually. Nuclear medicine is tremendously exciting because we're looking at molecular imaging, functional imaging, physiological imaging. And as I mentioned, we have so many isotopes that are out there, and a respectable number of those can be used in nuclear medicine. And what's more is that those can be used to bind to many, 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 many different kinds of molecules, each of which could be measuring different things. Okay, so carbon-11 in this example can be used to label totally different molecules, which are measuring totally different things. So it's very, very exciting, actually, the kind of things that you can do. So here's just an example in oncology. Fluorodeoxyglucose, this is radio-labeled sugar. Well, there's increasing uptake in a tumor because of the increased metabolism, whereas in normal organs, it comes in and then it leaves. Whereas because of this process of phosphorylation, it kind of gets trapped in highly metabolic tissue, specifically tumors. This is a phosphorylation step. We have fluorodeoxyglucose phosphorylates into fluorodeoxyglucose 6-phosphate, and it just gets trapped and it accumulates in the tumors. This is the bread and butter of PET imaging in the clinic these days. But again, this is not limited to just oncology. You could, first of all, as you know, there are many different, over 100 different neurotransmitters, right? And you could try to study these. And neurotransmitters are interacting with receptors or transporters, and therefore you could be studying neurotransmitters if you're able to, for example, create certain molecules that bind to receptors. Imagine you've got dopamine receptors, D2 receptors. If you create certain molecules that compete with dopamine that also binds to dopamine receptors, you could be, for example, indirectly measuring how much dopamine is in this space. So you could be labeling receptors or transporters and therefore studying the dopamine levels. For example, this is very, very popularly used in Parkinson's disease and others. So here, again, you could be doing imaging of the neurotransporters or neuroreceptors, and through that studying many different aspects of neurotransmission. Just showing an example, many things commonly used in different diseases, including Parkinson's disease, as I mentioned. So you've got dopamine that is being delivered through the vesicular monoamine transporter. So you could be imaging that, or you could be studying the dopamine receptors, or you could be studying the dopamine transporters. And through that, studying what's happening to the neurotransmission in the brain, what is going on with the brain of a Parkinson's disease patient. those years when I was at Hopkins, we were looking at a lot of different things, different aspects, different radiopharmaceuticals for brain imaging. So here are many different examples of imaging dopamine receptors, the dopamine transporter, the vesicular monoamine transporter, serotonin, mu opioid receptors, the cannabinoid receptors, so-called marijuana receptor, many different things. And so you could be studying those using different radio-labeled molecules. Like in this case, for dopamine receptors, you could be using raclopride or methylphenidate for this, depending, again, so for different neurotransmitters and different neuroreceptors and neurotransporter phenomena, you could be using different molecules. So it's very tremendously exciting, and you could be studying this. Cardiac applications, myocardial perfusion imaging is very popularly done, as you know, in our field, in nuclear medicine imaging. So I won't go through those details, but there's tremendous value, as you know, in myocardial perfusion imaging using SPECT, for example, and PET imaging. Okay, so let's actually talk a little bit more about this. How do we do nuclear medicine imaging? Any questions so far? Feel free to stop me, please. You can see that I'm quite excited about this field because I feel that it's often underestimated. You're more than welcome to come and visit our facilities. I'd be delighted to show you around. If you still haven't seen the imaging facility here we have at BC Cancer, particularly to nuclear medicine imaging and therapy. So let's talk about single photon imaging. PET imaging is dual photon imaging, anti-parallel photon imaging, where there's two photons. But let's talk about single photon imaging. That gives you planar imaging, gamma imaging, and also in the case of tomography, it's going to give you SPECT imaging. So isotopes are emitting single photons here. Photons are recorded outside the body. You've injected something or inhaled something's in your body, and the photons are exiting your body. The gamma rays are exiting your body. So they have a certain direction. They have a certain. You need to have a certain. You need to have the proper energy resolution to be able to know what the energies are of these things. So to remove things that have been scattered, that are complicating things. And you really need to be recording as many photons because, otherwise you're going to get very noisy images. So this thing is called a gamma camera or a scintillation camera or an anger camera. You're going to be learning more and more in this presentation about why we call this a scintillation camera, why we call this anger is the name of the person. Why is it called the anger camera? Like, what did Mr. Anger actually do? So let's talk about these more. At the beginning, we didn't have a gamma camera in this sense. And what we used to have, there was this invention by Benedict Casson at UCLA, where basically he had this kind of a design where he was only imaging a single point. So it's not good enough at the same time to be imaging a field of view, but only imaging a single point where all these collimators are focused on this point. So all photons coming out of this point, he would have been able to see. So if he's doing that, then he has to be moving this over the body in order to image, because at a given time, he's only able to acquire a single point in this field that is in front of us. So he used to use one or two large detectors, maybe one at the top of the body, one at the bottom of the body. And this dominated nuclear medicine in the 50s and 60s. So again, it's a large piece of lead, basically. Okay, so the scintillator, the thing that is able to actually detect these gamma rays, that's sodium iodide, for example. That's a scintillator. It's a crystal, a scintillator. But at the front of it, you've got these focused lead collimators that are sort of saying, I can only measure things coming from this point. Anything else from this here, I'm not going to measure because my collimators are going to reject you. And then again, it's a rectilinear, so you kind of move like this, back and forth to you until you cover the body. So, section imaging. So this used to produce a coronal plane. This is very old stuff. It's just a historical thing. Thank God we don't do this anymore. But this is the historical innovation that, of course, we built on top of. But let's talk about. So these are the kind of images that we used to get. You see the feel of a rectilinear sort of going through. And this is actually why there was this joke that nuclear medicine is just playing with the letters here, is unclear medicine, because the resolution was not good enough. I mean, this doesn't look good at all, right? But we had a major invention by none other than Mr. Hal Anger, who invented in the late 50s something in Berkeley, California, that we are now calling the gamma camera or scintillation camera and camera. The beauty is, at a given time, it's imaging a whole plane, a whole field of view, not just a single point. So how did he do that? And this idea to this day is being used. So let's go through that. The gamma camera, how does it work? If I have to break it down, I would say these are the steps. Here's the patient. You've got a collimator, not like those focused collimators that we saw. It's a collimator that actually is parallel often. So anything that is going at 90 degrees or give or take can enter it. You've got a crystal, you've got a photomultiplier too. So how does this actually happen? So let's look at it another way. You've got the patient, you've got these parallel collimators, you've got the detector or the crystal or the scintillator, and after the photons pass through these collimators, it's going to detect them. And then you have some electronics at the back that amplifies the signal, converts essentially these gamma rays being detected ultimately into electric signal that you obtain. Yeah, so you've heard of the term scintigraphy, also known as a planar scan or a gamma scan, or gamma or planar imaging. Basically, it's planar. It's like the equivalent of an X-ray, right? So this has been used for diagnostic imaging, for example, to visualize a 2D projection. It's like a 2D projection. So it's analogous actually to plane or projectional X-ray radiography. Very analogous. The difference being that here the source of the radiation is inside the body, whereas in X-ray radiography, as you know, the source is outside the body, it passes through the body. But it's very analogous to it. So that's scintigraphy for you. The difference is that, again, in our field, in nuclear medicine, we're dealing with emission, whereas in X-ray imaging, we're dealing with transmission because the source is outside the body. But we want to move, if you want to move from 2D imaging to 3-dimensional imaging that you actually visualize depth, then you need tomography. So in this case, you're not just acquiring at a fixed angle, you're going to be rotating around the body, so you're acquiring at different angles. So this is called emission computed tomography. You've heard of computed tomography, CT, but in our field, we call that emission computed tomography. To emphasize that, again, the source of the radiation is inside the body. So for emission gamma rays, this leads to single photon emission computed tomography or positron emission tomography. And again, you've got the radiation coming from inside the body, you've got planes, and the planes can, for example, rotate around the body, SPECT image. But if it's transmission projections that are collected, well, that's transmission computed tomography, or commonly known as just as computed tomography. So if you're dealing with X-rays, then we call that CT imaging. So again, it's very analogous. Scintigraphy is analogous to planar imaging, whereas PET and SPECT imaging are analogous to CT imaging because they're tomography. So it has many applications for assessment of bone, lung, heart, thyroid, kidneys, many different things. And let's talk about the crystal itself. Crystal, or the scintillation crystal, sodium iodide. It is a sodium iodide. It is doped with something, thallium. And that's almost a technical detail. But basically, which enhances its performance, enables it to do what it does. I don't want to go too much into detail here, but basically, one thing you have is that you tend to coat the edges of it, edges of the crystal, with reflexive material, because once a photon comes in, sorry, a gamma ray, once a gamma ray comes in, here in the crystal, it creates so-called scintillation. Just hang in there with me. Scintillation is almost, to really boil it down, it means you absorb that really high energy radiation, gamma ray coming in, 140 keV, for example, coming in. You absorb it through some kind of molecular excitation, and then that molecular excitation comes back to the sort of the base level, and it emits much lower energy photons, but many of them. And so it scintillates, right? You can actually see it visually. And so these much less energetic photons, they may start going in different directions. So you may be coding this so that they're not leaving the system, but they end up in the PMTs. And what the PMTs do is that they absorb those photons, those scintillation lights, and they amplify, they convert them to electric signal. We'll get there. Just hang in there, hang in there. So scintillators, how do they work? You have incoming gamma ray, which is highly energetic, that loses its energy in the scintillator through certain mechanisms. And those mechanisms end up exciting the molecules of the crystal. And those molecules, as they're excited, when they come back to the ground state, they glow. And that glow is the brightness of it. The number of photons they emit is proportional to how much energy was. So you can actually know what was the energy of the photon that I just absorbed. So what are some important properties of a scintillator? Well, they have to have very good stopping power. They're very energetic, hundreds of kilo electron volts coming in per ray. You got to be able to stop them. So you got to have dense material. You got to have something that when it glows, or when it gets excited and comes back to ground state and glows, that doesn't take too long. Because if it takes too long, it's almost like the processing time is too long, and so I'm not open to more events coming in. So you want it to decay quickly, so you're able to accept more events coming in. Linearity is a technical alternative. You kind of want to be able to map, what was the energy of the thing that came in. Conversion efficiency. Not only do I want to absorb you, I also want to convert you into scintillation light, lots of it, so I'm able to detect and know how much was the original energy. It has to have good spectral distribution, meaning the energy resolution should be good. So let's show you some examples. So this is the energy of the incoming ray. This is the number of, this could be here, for example, the number of photons at different energies that you're detecting. The original source was here. But what you end up getting is not just a single spike. You're getting a whole range of stuff that are kind of strange. Like, I really don't want to be seeing stuff here because my incoming energy was here. So I do get a bit of a broadening. That's like the energy resolution of the system. But what are all these things here? These are all the unwanted stuff. But we'll come back to that. But the energy resolution is this. You want this to be as small as possible. The percent full width at half max, you want it to be as small as possible, because that allows you to really know what was the original energy very well, so that you can reject all these weird, unwanted, scattered events. Okay, so you measure the width at half of the maximum, and in this case it's 46. So 46 divided by 662. If it's the original source was 662, and this example tells you that this kind of at this energy and with this kind of a whatever detector, I have a energy resolution of 7%, which is actually pretty good. So many different scintillators are out there. Sodium iodide I kept mentioning, used for single photon, but these are example of scintillators using PET imaging, because PET, the energies are much higher and you need better scintillators. So, but you see how the density is here, but whereas for PET, we really need to use denser material because we want to stop that really energetic light. And that's why one reason PET scanners are more expensive, because you got to have denser material. You got to have more expensive crystals to absorb the light. The effective Z or Z number is important. What else do I want to really mention here? The energy resolution, look, they're typically in this kind of scale. Look at the decay time, so in nanoseconds. So like, for example, LSO, which is very nice, right? Because it's not taking too much. It's almost like the processing time is not that long. And the attenuation coefficient, essentially, you see how it changes. So obviously these things are better than sodium iodide at this very, very high energy, which is the energy in PET image. So this is why sodium iodide is not a good crystal for PET imaging applications, but it is great for for SPECT single photon image. So if somebody was asking you, give 2 reasons why LSO is preferred to BGO. In PET imaging, people used to use BGO, but then they started using LSO. Let's look at it together. What are 2 reasons why LSO is better than BGO? You see the densities are almost the same. Effective Z values are not that different. The attenuation coefficient is almost, in fact, slightly even lower. But there is this number that is really higher, the so-called conversion efficiency, which says, let's take sodium iodide as the reference. You know, the number of photons that are emitted in this scintillation phenomena. Well, LSO produces a lot more photons. So the photon yield or the conversion efficiency, essentially for sodium iodide, is for every kilo electron volt, you produce 40 photons. So if it's 140 kilo electron volts, 140 times 40, that's a lot of photons that you produce. Right, so 140 times 40 is around 6,000. So for every single ray that comes in, this produces about 6,000. So let's call that 100%, like just as reference. LSO produces a lot more than BGO. So a lot more photons are created. So that allows you to do better imaging, better signal, less noise. So that's one advantage. The other advantage is you see the energy resolution is smaller because there are a lot more photons created. Turns out to actually give you better signal to noise ratio, better energy resolution. So the correct answer here would be better.
See?
Better conversion efficiency and not stopping power. So the stopping power is
okay.
No, good guess, good guess. Faster decay. That's right. So the absorption is not better. The stopping power is not better, but the photon yield, what it produces, is better, and it is faster. Was that Tracy? Thank you for answering. So
Ali.
Oh, what's you're what? You're with Ali?
No, it was me, Ali.
Oh, Ali. Oh, I'm sorry.
Okay.
Okay. Good. Thank you for that. Thank you for answering. So B. Okay. So multiplier 2. So what on earth are PMTs? So PMTs, once you're producing scintillation light, so again, you stop the really high energy photon, convert it into this much lower, but lots and lots of photons. Well, photons are entering here, but you want to get a signal that is electric, not photonic. Like the electric circuits work by electrons, not by photons. So then you use a PMT for that. A PMT takes the incoming light, has a photocathode that basically uses a photoelectric effect. That photon comes in, electrons go out. This is a photoelectric effect. This is what Einstein won his Nobel Prize for, because he studied that effect. So you produce these photons, and then you have these diodes that amplify the signal. Okay, so here are examples of the PMTs. And again, so you have a photocathode, and then when struck by light photons, the electrons are emitted from the surface. So this is a photoelectric effect. And then these photoelectrons are then attracted to these metal plates, which are called diodes. And the diodes amplify them. Now, typical diode material, like examples here, essentially through this thing called secondary emission. It's a phenomenon. It's like you've got this surface, you hit it with a single electron, it releases like 3, 4, 5 times as many electrons. It's a secondary emission. Electron to electron, but it's amplifying of electrons. So you enter here, let's say with a single electron, amplified, until here you get a substantial signal that is detected. Because if you only had a single electron emitted, you couldn't, that's not going to give you enough signal. But PMT is amplified. And so you apply a lot of voltage, like let's say 50 to 100 volts per dynode. So if you have like 10 dinodes, you're gonna need like 1,000 volts here. So you need high voltage supply. Okay, so and so you get significant amplification. Now, one of the issues is that PMTs can be influenced by magnetic fields. Why? Because remember, you got electrons moving. If an electron is moving and there is an magnetic field in there, the electrons can be distorted in their movement. An electron in the middle of an electric field can move in weird ways. Or actually there's laws for that. So they tend to use so-called mu metals, which is kind of, here's an example, like nickel iron alloy, as an example, to increase the permeability. So here's a measure of the permeability. They have very high permeability, and what they do is that if you have a magnetic field for whatever reason here, once you use these, they kind of redirect the magnetic field along this direction, so they lessen the field's influence on the items. They kind of shield the PMT from the Earth's natural magnetic field and other things nearby. Now, they cannot do magic if there's just too much magnetic field. Like if you do PET MR imaging, which is something people do, then this is not good enough, because a magnetic field like 1, 2, 3 Tesla is not going to be, is too strong for this. But for lower ones, it's good enough. So here's a question for you. If there's a magnification by a factor of 4 at every PMT dynode, and you have 5 of them, what is the total amplification? How would you do this? Even if you don't have a calculator, how would you do this?
Is it like 4 to the 5?
So is it 4 to the 5 or is it 5 to the 4? Which one is it?
If there's a magnification. Oh.
You might have said it right.
5 to the, I don't know. 5 to the 4?
No, I think you said it right before. Because it's like at every dynode, it gets multiplied by 4. So 4 times 4 times 4 times 4 times 4. So you get multiplied by a factor of 4, by magnification of 4, 5 times. So it's 4 to the power of 5. Which is, I think, what you said initially, right?
Yeah, so D.
Yeah, so it would be D, exactly. So the answer is D, because 4 to the power of 5 is 1,000. But this is just a number. In reality, it's quite more. In reality, it's more like not a factor of 1,000, but it's more like a factor of 1 million, because you have more than 5 dinodes. You have more like, let's say, 10, and the amplification is actually more than a factor of 4. That was just a toy example. But really, the amplification tends to be around 1 million or more. But this toy example, it was around 1,000. Okay, so thank you for that. So, okay, so we've talked about the scintillator, the thing that stops the original high energetic gamma ray, converts it to scintillation light, PMT, which converts that to electrons and gives you high level electricity or electric signal, and the voltage supply that's needed to achieve that around 1,000 volts. But let's now talk about other stuff. I noticed that this is for gamma ray. For PET, it's very similar. The phenomena is the same, except in PET, we don't have like a detector like this that rotates around the patient. You'll see why we have to do this in SPECT, but in PET, you can actually build detectors all around the patient like a ring. Even in SPECT, you could sort of do it with certain new novel designs. But traditionally, in SPECT, you've had a planar detector which rotates around the patient. Whereas in PET, you could surround. But the ideas are, the rest of it is the same. And also the principles of a well counter are highly related to this. What's a well counter? It's a very high sensitivity device to measure low amounts of radioactivity. let's say you do blood sampling. Imagine you injected radioactivity into the body of a patient, and you just want to measure how much radioactivity there is in their blood. So you take little small samples, blood samples, so there's very little radioactivity. So how do you measure that? So you have this so-called well counter. It's a well, but this whole thing is a scintillator, one big, massive, highly sensitive scintillator. You dig a hole in it, and you put your radioactivity here. Well, it's so sensitive to this because almost all photons emitted, all gamma rays emitted, except the ones that are directly exiting the well counter, are going to be measured by it. So guess what? This is going to be highly sensitive. But the principles are the same. You've got a scintillator, and then at the back of it, you've got a PMT, a PM tube, a PMT. So the electronics for a well counter are also in a sense similar. And finally, probes, so-called surgical probes. Imagine you've injected a patient something just to see how much stuff is, in this particular tumor, or to detect where the tumor is in the body during the operation, or to see whether you've successfully removed all of it. So probes are these things that I'll show you, but the principal operation is the same. The only catch is you're not surrounding the patient with it. It's just a single crystal. And this single crystal in the probe is basically matched to a PM tube, to a PMT, and in the back of it, you have got electronics. So it's a very similar thing, but you're just having this probe that you move around and see what's going on. So again, small detector and a collimator here, just so that you get only photons coming from a certain angle, not from outside of the field of interest. So probes, of course, are exciting. So nuclear medicine is not just about scanners that we're used to. The probes are quite valuable. Surgical procedures. You could do lymphatic mapping, or known as sentinel lymph node biopsy, which is minimally invasive. Looking at things like melanoma in this example, and this audience is, I think, very familiar with that, or looking at breast cancer. So it's a very, very valuable technique. You've got the probe here, sort of making measurements of the sentinel nodes. And newer probes are moving towards other kinds of detectors, so-called semiconductor detectors, which are more expensive, but you only need a single detector. So even if it's more expensive, it doesn't really matter for a single detector. So people are moving from scintillation detectors to semiconductor detectors, but the principal operation is the same. Okay, so let's talk about some more details. Remember how I said you got all these weird events, low energy things that you measure, and you really don't want them. Well, how do you even measure them, and how do you eliminate them? Like, imagine a photon or gamma ray in your body. Before it leaves your body, it scatters in your body, and which lowers its energy, and you end up detecting something coming from the wrong angle because it got scattered. Could totally deceive you. How do you eliminate such an event? So you need to be measuring the energy of the gamma rays that are coming in. So how do we measure the energies of the gamma rays? So in fact, the truth is that we can, as I just mentioned to you before, because the number of photons that you get generated from a scintillator is proportional to the original energy. So we can measure the energy. But another question is, why do we get so many different energies? What does that distribution even look like? So let's understand all these phenomena that are going on. So imagine you've got a source that is entering the crystal. This is your scanner. Well, ideally, this thing enters here, all of the energy is absorbed, scintillation light's produced, and great. But there's a whole bunch of other things that can happen. For example, you could enter the crystal, but you're not fully absorbed by the crystal. You scatter, but then you're absorbed here. Well, that's okay, because these two events are still absorbing the same detector. But what if you enter the crystal, some of your energy of that highly energetic photon is absorbed, but not all of it, and the rest of it leaves the detector. So you've only you've only acquired or captured some of the energy, you've lost the rest. So you're going to look at a lower energy photon, or you're going to think that the original gamma ray had lower energy than it actually did. It's going to mislead you. Or what if before you enter the crystal, you enter some kind of a shield around it, you scatter, and then here you have a lower energy gamma ray that's coming in, and therefore you're misled. So many opportunities to be misled. But guess what? We can eliminate most of them, or many of them. So imagine, questions welcome. Imagine that you've got an original gamma ray that has 662 kilo electron volts in this example. This is what you actually measure, which is mind-blowing at first, but it's okay. We're okay. We're going to deal with this. You have all these weird things showing up, whereas you really only expected to see something at 662. Sure, we see a little bit of broadening simply because nothing is perfect, right? We have limitations. We have noise. So you're going to get a little bit of noise. But okay, we wish we only measured this, but we've got a whole bunch of things here. So let's try to understand what they are. But the good thing is at the end of the day, we could put upper and lower energy bounds and reject all these events. But let's first try to understand them. So here you see things like X-rays. Okay, so these are not actually gamma rays. Some of these are X-rays. We'll see that in a second. K-shell X-rays, for example, from lead. Okay, so remember, you have lead shielding, and you have lead shielding, and through absorption of stuff through the lead, you may release X-rays. So that can totally mislead you. So you've got sodium or lead, sorry, lead X-rays here, for example, in the range of 80 to 90. So that could be the peak here. Energy resolution, we already talked about, so I won't go over that. You can be putting, there's other things. Oh, do I go over it? No, actually, let me go over some details here. So this is the lead X-ray that I just mentioned too. There are things like so-called Compton edge. You could be, or a backscatter peak. You could be, for example, entering the crystal and being backscattered and only conveying and releasing part of your energy. Okay, so if that happens, depending on the angle by which you scattered, you could get a range of energies that are in this range. This is the maximum value. We call that Compton edge. This is the lowest that you could, for example, be having in this example. So Compton edge and the backscatter peak. Okay, so backscatter peak, I won't go through the details, but basically you could be, because of scattering, you could be getting events that are in this area, whereas you should be declining those events. So to do that, we would put a energy spectrum or put a upper and lower energy range. For example, we would say I only will be accepting a 20% window around my photo peak. 20%, and nothing else I will accept. So all these stuff I will be rejecting. So here's a question for you. Let's look at technetium-99m, which has a photo peak energy, which is the incoming gamma ray energy of 140 kilo electron volts. If I put a 20% energy window on it, what is the range of energies that I'm accepting? Which one of these four is it? Can you work it out?
It would be B.
So it's always, of course, with me, now you're learning, I'm asking trick questions. The 20% is from the upper to the lower. So it's not from the middle. So it's really more like when I say 20%, when we say 20%, we mean 10% at the top and 10% at the bottom. You know what I mean?
Okay. Yep.
Yeah. So because of that, 10% of 140 is 14. So it would be 140 plus 14 and 140 minus 14. So it's actually D. So these are going to be the energies we're going to be accepting. We won't accept anything else. Okay. So we could be doing things like dual peak imaging. So for example, when you could be injecting two different, this is the beauty of gamma single photon imaging. You could be injecting two different things into the patient with different energies. Let's say technetium-99m has a photo peak at, the main energy peak is at 140 keV, whereas indium-111 gives you 171. These are two different energies. So you could be putting two different energy windows simultaneously imaging two different radiopharmaceuticals that are co-injected, for example, which is amazing. but you got to be careful, because if the peaks are too close to each other, they may cross-contaminate due to the blaring energy resolution. Sometimes people, instead of putting like a 15 or 20% energy window centered, they might put it like left centered or right, or instead of centered at the peak, they would put it a little bit to the right or a little bit to the left. In this case, they would put it 10% from 171 all the way above it, so not below it, so that there's less contamination. Just as an example. Okay. So let's go through this. We can take a break a bit later. So the gamma camera has a number of principal operations. We already really talked about this. I'm just going to keep mentioning some of these. We need the, okay, we haven't talked about collimators much, but we've talked about the crystal or a scintillator. We've talked about the fact that you need a PMT, a photomultiplying tube, and the back-end electronics, we haven't really covered that much. So we're moving this way, right? The patient is here. Collimator basically blocks photons that are coming at bad angles. Doesn't want to be confused. It only accepts photons coming at 90 degrees. And we talk about PMTs. So there's a whole bunch of electronics which I really won't go into. You know, essentially imagine that at the end of the day, you've got your PMTs, and you can really figure out which PMT obtained your signals. So you know the X and the Y coordinates. You would know. And when you know the X and Y coordinates, so we call those X, forget about this X minus, X plus. Those are just old, you know, electronics literature, but just X and Y, you know the coordinates. You know which PMT obtained the signal. And the Z or the Z signal is basically, it's not the Z coordinate, it's just the energy. X, Y, Z. X and Y are the physical coordinates. Z is the energy. You know the energy. So the beauty of Anger, and this is one of the key contributions of Mr. Anger, which really allowed this to happen. The beauty of Anger logic, or you know, what exactly is it? Conventionally, this is what you would get. For every PMT would have to be paired with every crystal, and so you get this kind of resolution. But with Anger logic, you get a much, much better resolution. So how does it actually work? The location of each interaction is determined by combining signal from multiple PMTs. So think of it this way. Imagine the original source of light was here. The scintillation crystal is producing a lot of different signal, but guess what? Not all of it ends up in this central PMT. Some of it ends up going to these nearby ones. Now, normally you wouldn't like it. You're like, oh, that's not good. They're ending up in different PMTs. But this is good because you could take the signal from all these PMTs and averaging them and figuring out what is the exact position even within a PMT. Normally, you wouldn't know where within this PMT you detected your signal here. Like, this is your event. Look at this event. Normally, you wouldn't know where along the PMT you got the signal. But now, because some of the signal, remember, you may have 4, 5, 6,000 different photons being generated from a single gamma ray coming in. Well, some of them end up here, some of them end up here. And when you average them and weight them, you would know where exactly within this PMT you obtain this. So this is Anger logic. It's kind of a very cool technique. So again, going back to this, the original signal is coming from here. So most of the photons end up in this PMT, but some here, some here, some here. And by averaging all these energies and weighting them, you would actually, by measuring all these PMT signals and weighting the amount of signal you receive, you can actually identify where within this PMT this event is aligned with. So you go from a resolution of 1 PMT, which is not impressive at all, to a sub-PMT resolution where you can get much, much finer. So that's called Anger logic, where you use nearby. It's counterintuitive, actually. You let the signal spill to nearby PMTs too, not the one-to-one mapping. So with the help of this community of PMTs and averaging, you would know finer details about where the original signal was. Again, just to emphasize, if you start from here, it's much less likely you're going to get a signal in this PMT. Much more likely you're going to get them here. And by averaging this, you can sort of figure out, oh, I'm slightly here to the left of the center, which you wouldn't have been able to measure.
So this, just to clarify, so you're taking like dead center of the average.
You're taking the dead center. What do you mean by dead center?
I don't know. I just going off of the image that you were showing with the circle in the middle.
Here.
Yeah.
So you actually average all this signal, and it would tell you that in fact it is not at the dead center of the PMT, that it is slightly off of the center.
Okay.
And that's why you can go from a resolution of not knowing where within the PMT you are to actually knowing where within the PMT you are.
Okay.
It's kind of a funny, bizarre thing, actually. Like, look at this signal here. If I'm getting all these different signals, imagine I'm getting 10 photons here, 20 photons in this PMT, 40 in here, 60 here, 35 here. If I average those, and if I average all those signals by the position of the PMT and the energy or the number of signals I got, I would conclude that I was not at the exact middle of this PMT, but I was slightly to the left of it, because this PMT next to it got a little bit more signal than this PMT to the right of it.
Right. Okay. Okay.
Yeah. So that's kind of a cool thing. Sometimes, you know, in life, you get something that looks worse, but it's actually better. You know, these things are spilling to nearby PMTs. Well, how can this be better? But it is better because nearby PMTs are giving you more hints about what's happening. I mean, that's a bad analogy, but imagine you've got nosy neighbors and you've lost something in your home. You don't know where on earth it is, but your neighbor to the right hears your cell phone better than your neighbor to your left. So you conclude that my cell phone is not in the middle of the house, but it's more to the right of the house because my neighbor's listening or hearing a bigger sound, something like that. And then you can do image formation, because remember, based on the position within the PMTs, you would say, oh, I just got a signal here. Oh, I just got a signal there. So you map them. For every gamma ray that comes in, you put it here or here or here or here or here. And it depends, of course, on the number of pixels that you have. The more pixels that you have, the finer the resolution, et cetera, et cetera. So given the fact that we can measure the energy of the signal, because the more the energy of the original gamma ray, the more scintillation that is being produced, the more the glow, you can actually eliminate some low energy values. Like, you know, you really should not be measuring 50 kilo electron volts. Like, this original event was 140 kilo electron volts. At best, it might have become 10 or more or 10 less because of, you know, limitations in signal to noise ratios, but it should not be 50 kilo electron volts. So you will be rejecting all events that are too low in energy. So you can do energy selection. Now, how do we pick directionality? So let's talk about that a little bit more shortly. But again, you would put an energy window around this and eliminate all these other signals that are coming in. But let's talk about collimators. Collimators allow you to control the energy. Imagine you've got a source here. The collimator tells you or allows this photon to pass through, but not these ones. And why is that? Because imagine you don't have any collimators, and you've got this is your source of, and this is like the human body. Let's imagine this is like some tumor in the body, or some organ in the body that with uptake. This is a detector. Well, any signal from anywhere in this organ could go in any direction and create this big blur, and you don't know what came from where, and you cannot visualize this. But if you put collimators that say, I will only accept you if you're coming at exactly 90 degrees, give or take a few degrees, I can better map where this event came from. I can back project it and know where it came from. But here, if I detect something here, I don't know where it came from. It could have come from this angle. It could have come from this angle. This angle doesn't allow you to do things. So unfortunately, you have to do a bit of a sacrifice. You have to put a collimator. Collimators are good because they only accept certain angles, but they're bad because they kill a lot of signal. This event has some value, but we had to kill it because we want to only constrain this to things coming at normal angles. So collimators are very common. They're made commonly from lead, whether it's lead foil or cast lead. So here's lead foils, cast lead. We won't go through those details. The walls of the collimators are called septa. Sometimes signal, unfortunately, does penetrate the septa, so that's a limitation. But you want to keep that to very low percentages. So here's an example of collimators. I can imagine if something's coming from above, it will only make it if it's really above it, but not going at an angle. We do have other kinds of non-parallel hole collimators, like converging. If you want to look at a small field of view and make a big image of it, so get better resolution, because looking at smaller things. Kind of like the original Casson thing, scanner, but that was focusing on a single point. This is focusing on like a part of the small organ, for example. You could have diverging too. Like imagine if, and people really don't use this anymore, but imagine you want to image the entire body in a single detector. So you could do that. Nowadays, because detectors have become bigger and bigger, if you really want the whole body, you just do multiple scans. There's also pinhole collimators, really used a lot in small animal imaging, for example, but also in brain imaging, where you could get really significant amplification. Won't have time to go through these details, but parallel hole collimators are the most common. You'll be seeing this is where a lot of the quality assurance is happening with and without these collimators. The size of these holes and the length of the collimators is going to really have a lot to say about the sensitivity and the resolution of the system. So I'm going to ask you a question. If I make the collimators longer, do you expect the sensitivity of the scanner to drop or to increase? What do you think? Making collimators longer, which means almost more intrusive, more hardcore in some sense. Like what because it's, well, I don't want to say it. Would it allow you to accept more events or less events?
You'd accept less?
Yes. So it lowers the sensitivity. So then you would ask, why on earth would you ever want to do that? Because it turns out it improves resolution. Because turns out that if you make this even longer, if an event is slightly at an angle and normally might have made it to here, if you make this longer, even that won't be accepted. So it actually makes the resolution better. Just hang in there with me. A general purpose collimator is what we typically use with this energy. So we call that low energy general purpose or low energy all purpose, LEAP. But to improve the resolution, we could do a number of things. We could make the diameter smaller. You could imagine why that would make the resolution better, because in resolution, smaller is better. You want to make the point source appear smaller. Or you could make the holes longer, which is what I was just telling you. But both of those those mean that you're using more lead shielding, because you're making the hole smaller, so thicker lead or longer lead, and that kills more signal. So there's always a trade-off between resolution and sensitivity. So to increase sensitivity, the holes need to be shorter, right? The holes need to be shorter or wider. And that results in a decrease in resolution. So there's a trade-off. And if you want to image like high energy isotopes, things that are not at 140, but in 200s or 300s, you need to be having thicker septa, because sometimes these highly energetic photons can penetrate. So you make the septa thicker. If you make the septa thicker, it's a heavier collimator and lower sensitivity, because again, it's killing more and more signal. So there's always a trade-off. But if you want to remember this, basically, resolution is better for collimators with long septa and small holes, but sensitivity is better for short septa and large holes. And turns out a twofold improvement in resolution, meaning getting 2 times smaller, which means 2 times better resolution, means you have to sacrifice 4 times in sensitivity. We won't show the math here, but just remember that. If you want to improve the resolution, like if you want to go from 4 millimeter, like 1 centimeter resolution to 5 millimeter resolution, right? So if you want to go from 10 millimeter resolution to 5 millimeter resolution, factor of 2 improvement resolution, you're going to have to kill 4 times as much signal, which is not great. There's a trade-off. So things to know about collimators. They're usually made from lead, typically hexagonal. The lead strips between holes are called septa. Parahole collimators project the same object size. They're looking parallel. They're not converging or diverging. And high energy radionuclides require higher energy collimators, meaning thicker septa. So let's try to answer this. You got a collimator A versus B. A has twice worse, poorer spatial resolution. Which one is more sensitive and approximately by how much? A is worse or B in terms of sensitivity? Or sorry, which one is better? Which one is more sensitive?
Oh, no.
Hang in there, hang in there.
A
You might have said it
has
right.
worse spatial resolution, so it's more sensitive,
Yes.
but by a factor of how much? Twice the worse. I think by a factor of 2, but I probably missed something.
It's twice as the twice, because it's twice
as
or
spatial.
if this is twice as worse, this will be 4 times as worse.
4 times,
So,
okay.
right? Because we said here a twofold. If
twofold,
you multiply
okay.
by 2, this will be 4-fold.
Yeah, okay.
So the answer, therefore, thank you for that, Ali. The answer is therefore B. A is worse in resolution, but it's better in sensitivity by a factor of 4. So it depends on the application, right? If your application cares about resolution, then you got to give up on, you're going to get more noise. But if your application really cares about the signal, the quality, the amount of signal, the reduced noise levels, then you might be getting poorer resolution. So here's a question. Is this true or false? Deterrence to improved resolution or spatial resolution in the clinic for the gamma camera are limited injected activity and scan durations. Is it true that a deterrent, an impediment to us getting better spatial resolution in the clinic is that we can only inject our patients with a certain amount of signal and we can only inject them for a certain or limited duration of time? Is this true or false? What do you think? It's a weird compounded question.
I think it's false.
Why?
Because it has more to do with the collimator.
Right. So let's work through this. If you want to get improved spatial resolution, Ali, what does it mean in terms of collimator or in terms of sensitivity?
It means that the sensitivity will be not as good.
Right. But imagine if you are allowed to image a patient for a very long time. Even though sensitivity in this device is poor, but since you're getting more and more and more signal because you're imaging over a long time, you can sort of make up for the loss of sensitivity.
Okay.
Or you could inject more stuff into the patient. Imagine you didn't have ethical, safety concerns. You could inject as much. You could make up for the loss of signal by just injecting more into the patient.
Okay.
So technically, some way that we amplify the signal to noise ratios in patients, so we make up for the fact that we don't have great sensitivity sometimes, is we just inject them more or we scan them for longer. But there's a limit to this. You cannot inject a patient too much, way too much, and you cannot scan them for way too much for practical reasons. Therefore, if these concerns were not there, we could be getting very good spatial resolution because we could be designing collimators that are awful in terms of sensitivity, but fantastic in terms of spatial resolution. And we would make up for that terrible sensitivity by just scanning forever.
Okay.
But we can't do that. So this sentence, it's a convoluted sentence, but it's actually true. And that's why you might hear that there are some MRI protocols of carcasses or things of the sort, where they get amazing spatial resolution because they scan the carcass for like 12 hours or 14 hours, overnight MRI scan. You get like sub-millimeter resolutions that are mind-blowing, but you can't do that with real-life patients. Okay, and collimator types are different, as I mentioned. There's parallel ones. There's pinholes and converging have somewhat similar properties in the sense that they make the image of the object bigger. They make the image bigger, therefore they have better resolution. Like even the tiny detail can be amplified. Diverging, the ratio of the image to the object is actually less. So you could be imaging like a whole body in a single small detector. Depends on the application. Just a quick comment about this, and then we're gonna take a break. Pinhole collimators are like a pinhole camera, actually. Like you've heard of pinholes. They do invert the image. Unlike everything else that we're having here, pinhole collimators invert the image, but that's okay. So this has been used in the past to examine small objects, because you really tune into an object or a small animal. Tremendous applications actually in small animal imaging, preclinical imaging. And now there's increasingly multi-pinhole systems where you don't cover just a single small area, you cover multiple areas and you patch them in a sense together. So there are really great, I mentioned brain applications, but also cardiac, dedicated cardiac, you could do using the concept of pinholes, where using each of these pinholes, you might be covering different parts of the body. Small animal imaging, where you're inserting the animals in here. Pinholes are covering different parts of the body. Super high resolution. You could do amazing stuff with super high resolution imaging with SPECT, right? So here's an example. You could be doing like multi-bed imaging, moving the mouse or the rat at different positions where it's being scanned by different pinholes and getting very, very good resolution. Like amazing resolution. Sometimes you could like, and these are old images. So sub-millimeter small animal imaging capabilities. And spanning beyond, to primates, to brain applications and things like this. And the convergent collimator, somewhat related to a pinhole. It used to be popular, but nowadays, because the resolutions of these collimators, of the just general resolution of even parallel hole, scintillator systems have increased, people do this less often. And diverging, again, I mentioned, you could be imaging a large object in a single scan, but again, not used that much. Because in new technology, you just make the detectors bigger and bigger and just scan them in a couple of bed positions. So if I were to plot this, there is a resolution of a gamma camera depends on the distance of the source to the collimators. The farther away that you are, it turns out you get poor resolution, because there's a chance that slight angles, even if you're not exactly 90 degrees and you're a bit tilted, you're going to make it, and therefore you're going to mislead the system. So as you get away from the surface of the collimator, you're going to get poor and poor resolution. You can sort of see that the resolutions have typically been around, we're talking about a scale of, let's say, 1 centimeter. Okay. Of course, things are getting better. But yeah, again, why is that happening? Just look at these. Imagine you got a point source here and a point source here. This point source, it turns out, these two events will be rejected by it. Here, these two events, just because of angular geometry, will be accepted. So a slightly wider deviations from 90 degrees will be accepted. So even though here you will be rejecting all these and only accepting a small range of deviation from 90 degrees from being normal perpendicular, here you give it a little bit more. And therefore, as you get farther away from collimators, your resolution gets poorer and poorer. And I want to show you this too. This is a plot of not resolution, but just efficiency or sensitivity, as we were talking about. There's a bit of a difference here. In a parallel hole, collimator, doesn't matter if you're close to me or farther away from me. Sensitivity is a sensitivity. The events are coming at 90 degrees. I don't care if you're close to me or farther away from me. I'm going to be able to see you. But it turns out that in a, for example, diverging or a pinhole system, as you get farther away, I'm going to do a poorer job of being able to see you. Yeah. So again, I'm just repeating same things: parallel hole, converging, diverging, and pinholes. Okay, you can sort of imagine, it might be hard to see, but you can imagine that a point being here is going to be detected better than a point here, converging, because if you're here, all of these can have an eye towards you. Whereas if you're here, some of these don't have an eye towards you. So converging is a kind of an exception. As you get farther away, your sensitivity increases. But that's an exception. For the rest of them, that's not the case. And parallel hold doesn't matter. If you're here or here or here, I don't care. I'll be able to see you similarly. So spatial resolution of a parallel hold degrades as you get away from it, as you have more distance to the collimator. All of them degrade, as we showed here. All of them degrade. But in this case, parallel hold, the sensitivity doesn't change, and converging improves, but the diverging and pinhole, the efficiency or the sensitivity decreases. And here's the magnifications. In a parallel hold, there is no magnification, but in converging and in converging, there is a magnification. In diverging, there is a, it's not a, you're kind of suppressing it. Now, pinhole depends how you think about it, actually. Depends where you are. It's a little bit complicated, so I won't go through that. Just to summarize, a converging collimator produces a magnified image. Diverging, a minified image. Pinhole is an inverted image, but it's also magnified. So I think this I need to really improve, because depends where you are. If you're really too far away, it could actually decrease it, but if you're at the right position, it could actually increase it. So this has to be fixed. Depends on the context, actually. Okay, now that I have to tell you, I'll tell you. If you're here, around here, you're clearly magnifying signal. Because imagine, if you got something that is this big, you're going to see it this big. But if you get too far away, you got a huge signal, you're going to get a smaller signal. So it actually depends where you are. Okay. And high sensitivity collimators have wider holes, and high resolution collimators have smaller and or longer holes. Okay, and finally, the modes of acquisition could be static. I already mentioned that. Could be dynamic. So you don't acquire just once, you acquire over time. And it could be gated, like you look at a beating heart and you get, let's say you subdivide the beats of the heart into 8 parts, and you keep acquiring from different phases of it, and you put them together. All right, so as mentioned before, you know, most commonly we have static imaging, and it's not truly static. I mean, you do have a acquisition time, but you end up with a single image, which is acquired over, let's say, a few minutes. But if you do multiple snapshots of the body, like one frame, another frame, another frame, another frame, so you're going to get multiple images. So therefore, dynamic images. And finally, we have gating. So let's talk about that a little bit. Example of gating, which is used to image repetitively moving organs. So cardiac and also respiratory movements. So you would be subdividing a cardiac cycle or a respiratory cycle into multiple bins. In this case, this is respiration. You could put a block over the body, or maybe even do like blockless imaging, where you somehow measure how somebody's breathing. You know, people have used Microsoft Kinect, you know, to image how the body moves, for example, different innovative ways. But the breathing cycle we can measure, subdivide it into, let's say, 5 frames, and you always bring signal from that 5th that is corresponding to that kind of a breathing phase. And or it could be 8, right? Or in this case, it's actually 8, not 5. So 8, and so you get 8 phases, 8 gates, 8 respiratory gates. And that the advantage is, okay, what is the advantage? Why should we, or why would anybody ever do gating? What's the advantage? Any guesses? Instead of just one big breathing cycle, just putting all of these together. Any guesses there?
You avoid the artifact of having the organ in a bunch of different shapes, I guess.
Yeah, exactly. So it's like breathing. Like imagine looking at a tumor, for example. As you're breathing, the tumor is moving up and down. So when you image it, if you're not doing gating, you get a blurred tumor. Now that you may even miss the tumor because if it's a really small uptake thing, you may blur out. So that's one, right? So you're trying to do essentially it's motion correction or removing motion degradation. But the problem is when you're doing this and subdividing this into 8 parts, each of these images is going to have, let's say, 1/8 of the signal. So you're going to get what? If you have 1/8 of the signal, what is that going to do to the quality of the image? What is it going to change? Gives you better resolution, less motion, but what does it degrade?
Sensitivity.
What's that? Did you say sensitivity?
Yeah.
Yeah, so yeah, exactly. So you're getting less signal per image, which gives you more noise. Less sensitivity or less signal per image gives you more noise. So the images become noisier. And this is one reason where right now in existing practice, let's say in PET imaging, this is really not being routinely used because at the end of the day, clinicians haven't liked the fact that the images are noisy. However, if you have a way, and there's active research in this area, you have a way to get these 8 images and register them like non-rigid registration. So you're going to get the original quality of signal because you're adding them together, but registering and adding, and you're getting sharper images. So there's very active research in this area. Yeah. So, and as the number of selected gates increases, you get less duration and less motion. So that's good, but you also get more noise per image. You got to find a way to deal with that. Here's an example. You got a 1 cc, 1 milliliter lesion on CT. This is with respiration happening. It's very hard to see, right? But once you do respiratory gating, you start seeing it much better. Like, of course, they show best examples here, right? This has been blurred out, whereas here it has not. But notice how the image is less noisy here than here. Here, the image is noisier. So you could be thinking of this as a tumor by mistake because you're getting signal that, so that makes it, you get, sure, you may get more true, you may detect more stuff, you may become more sensitive, but also your specificity may go down. Like you may start detecting false positives. So there's a trade-off. But there's a lot of movement towards data-driven methods where you use the original signal itself. You don't even use a block on the chest. You don't use external tracking devices, but use the signal of itself that you're acquiring to get a sense about how the body is moving and somehow doing stuff. So it's work in progress. It's a very active field of research. And it has been for a long time. We had hoped this problem would be solved, but I think from, sometimes how physicists don't talk to clinicians too much and vice versa. If people had been really talking and collaborating a lot more on different topics, things would have converged probably sooner. So we need to bridge those gaps. And this is why I'm very appreciative that you're taking these lectures and you're trying to understand the physics more. Some of the smartest people, when I was at Johns Hopkins University, the radiology department for about 13 years, some of the smartest people I know, MD scientists and physicians, they understood the physics behind what was going on. They would give us brilliant suggestions. We would tell them stuff. We would sort of have interactions. Similarly here, we have very smart, here in Vancouver, we have very smart people on both sides of the aisle, and it shouldn't be both sides of the aisle. We should be all together and integrated, and I think it's happening, at least in some places. So what are some of the aspects of quality assurance or quality check? There are all kinds of acceptance testing. How do you accept a scanner that is performing well? This is a part of our job, right? As physicists, that we do acceptance testing with different kind of fandoms, with different kind of required specifications. And after you accept the scanner, you also have to make sure it continues to work well. So you do routine QA or routine QC. And there are different organizations that talk about this. So a whole bunch of publications. I won't go through it. This one is pretty good. I would say the IAEA of the Atomic Agency is pretty good. So NEMA is this organization that creates very specific specifications on what are some of the things that are important in acceptance testing, for example. So we do intrinsic and extrinsic measurements. What does that mean? If you do some kind of quality assurance on a gamma camera without the collimator on it, we call that intrinsic measurements. If it's with the collimator also, it's extrinsic. And both are important. And of course, you can imagine the performance is degraded by adding a collimator. Collimator is there to kill signal, right? And does stuff. But we have to use a collimator. But anyhow, the extrinsic and intrinsic performances are different. So uniformity. You obviously want something that is uniform. Otherwise, you may see stuff that don't really exist in reality. So what are some of those uniformities? Linearity, we'll talk about this. Energy and flood. So if a gamma camera is opposed to a uniform flux of radiation, it really should look uniform. But there are some distortions. And once you correct for those distortions using these 3 corrections, hopefully you're going to get a nice uniform flood image. If you don't get a daily uniform flood image, something is wrong. You have to fix it. So nonlinearity is a first major cause of non-uniformity. And the point is that a PMT, I've mentioned PMTs a couple of times, the edge of a TMT responds to signal differently than the center of a PMT. Just an observation. So if you're here, you're going to be, the sensitivity to a point here is going to be different than a sensitivity to a point here. Okay, and remember, the position, the angular logic was based on how much signal you get in different places. If you're not taking that point into account, you might be thinking, oh, I got less signal here, therefore less stuff is here. But no, that's simply because the edge of a PMT detects stuff less than the center of a PMT. So if you don't correct for that, you're going to get these strange and weird shapes, okay? But we already know this. And so if you just make like, if you just image like line sources and you get this, you can correct for them. And you basically say, hey, if I detect something at this position, I'm going to add an extra X. If I see something here, I'm going to move it by this much. If I see something here, I'm going to move it. It's almost like a lookup table. It's very easy to do. So you have linearity phantoms. These are like LED shields with thin slits. So they're going to give you these weird nonlinearities, but then you look it up and you fix it. The second one is variations in the energy. Okay, so this is also caused by variations in the crystal. So the crystal itself, if you image stuff in a crystal, the sensitivities vary in a crystal. So at some place, you may be thinking, I'm detecting, 140 keV, but it's really because the sensitivity of the crystal is different. You're getting more signal. You think, oh, that means the original ray must have had more energy. But no, this is just because the crystal is not uniform. So again, you can correct for this because you know the truth. The truth is supposed to be 140 keV. So if I get a signal that is centered at the wrong place, I'm just going to shift it and fix it. So you fix the Z signal, the energy signal. And then the third part is efficiency of the detector. So after you do these 2 things, right? After you do these two things, you take care of the shifts in the energy and the position, you still may get some non-uniformities, okay? And then you can do count skimming or whatever. You just say, okay, after I did everything, I still get non-uniformities, and then you can still have a lookup table and fix that. So if you don't do these corrections, you may get something like this, which looks awful. I mean, sort of, right? This looks much better. So spatial resolution is another measurement that we make. It's a very, like, if someone tells you spatial resolution, you should probably know what that really means. And it's basically the ability of a scanner or a camera to resolve point sources or line sources, right? So, and this is performed intrinsically with no collimator and a point source. Or you could be putting line sources. So we could be putting a single point source and measuring that, and then we could be putting line sources to see how able we are to resolve these separations between these line sources. They talk about this thing called a minimum resolvable spacing. What is a minimum resolvable spacing between these lines? And that turns out to relate to the resolution of a single point source. There's some math behind that. So we kind of talked about this. You have the resolution of a typical LEAP or low energy general purpose or all purpose collimator is around 1 centimeter. And the collimator degrades the intrinsic resolution. So originally it would have been better, but once you added these, stuff happened. Okay, so in other words, if I attach a point source to a crystal, if I attach it, you will be able to see it very well. But once you start putting in a collimator, and also depending on the distance that you have to this, you're going to be degrading things. So and it depends on the geometry of the holes, overall resolution. So you've got intrinsic resolution, you've got collimator resolution. So notice this right now. If something enters here, I don't know if it entered here or here or here or here. So that defines, that almost defines the resolution. Whereas if I had attached this to the crystal, it would know literally, well, it's here. So I won't go through those details, but the point is that the overall resolution is worse than the intrinsic resolution. So, and there's multiple things going on. There is the contribution of the intrinsic resolution of the crystal, which depends on things like the crystal thickness, etc., the energy of the gamma ray, but also the collimator design itself gives you a certain resolution, and these two things compound together to give you the overall resolution. Because again, if you put a point source right here, that would give you the intrinsic resolution. But once you add a collimator, your resolution starts to become here. Right, so you wouldn't know where within this the point sources. Okay, so, and as we mentioned before, as you get farther away, as your distance increases, your resolution gets bigger, which means it gets worse. Okay, so we talked about that. The efficiency or the sensitivity of a gamma camera is important, because it affects the imaging time. Remember how I said, if we could image forever, this wouldn't really have a problem. This wouldn't be a problem, but we cannot image forever. Therefore, we cannot have a really poor resolution camera. So it's really going to define the noise in the image and the minimum imaging time that you need to get a decent image. So the efficiency is important. What is the efficiency of the detector? What is the efficiency of the collimators? Because collimators kill signal. If you make collimators really long or tall, they're going to kill more and more signal. Okay, so these are very important. So the efficiency, this is a mind-blowing number. It's almost depressing. The efficiency of a common purpose lead collimator, parallel hole collimator, is about this much, which means out of every 10,000 photons emitted from the body, only like 2 of them get detected. Now with pinhole cameras, this number is increasing, but we're looking at definitely less than 1%. More than 99% of signals being killed. Okay, so that's why it's important to build bigger cameras that are covering larger parts of the body, to come close to the patient as much as we possibly can, and to build more innovative, scanners. Okay, so that last term F that we had has to do with the energy resolution. Of course, you could make the energy resolution or the energy window bigger, but then that way, sure, you're getting more sensitivity, but you're also bringing in more non-wanted events. So here's a plot of the efficiency as a function of the energies. The higher the energy, your efficiency goes lower because the gamma rays are going to be so penetrating they could even pass through your crystal. So the width or the thickness of the crystal, the intrinsic sensitivity of the crystal increases as the width becomes bigger. That makes sense. So some artifacts that you might get uniformity artifacts. A non-uniform image could be mistaken for a clinical abnormality, and that's really bad, right? So that can result, there are many possible sources of error which result in non-uniformity. So what are some of the reasons that we get non-uniformity? The point is that this has to be checked on a daily basis. It's the most important QC test that is done on a daily basis. Now, this could be caused by human errors, like the human operator, the technologist sets the wrong energy window because it's 140 kV, but they set it to be 300, and so everything's all messed up. That's one example. This is a routine QC check of an extrinsic source that is used like a daily scan, but they use the wrong low energy collimator, okay, versus not. Okay, so using the wrong energy, you're going to get really different signals. Both images show some non-uniformity because the source was imaged with technetium energy window. Okay, so this one is because of poor tuning too. Okay, this one has crystal hydration issues. Okay, but there's a whole bunch of things going. So there's something actually wrong with these, but on top of that, the energy window being off creates issues. Okay, so so then how do we do? It's almost like too many things are gone wrong. There's something wrong and our setting is wrong. But sometimes a wrong setting done in different wrong ways can actually tell you what's going on. So if you put if you have crystal hydration, if you put a symmetric energy window, you get this. But if you put the wrong window, you start to see these kinds of artifacts. So that actually, in a funny way, this was hidden here. But once you put the wrong artifact, you start to see the wrong energy window, you start to see wrong things in there too, right? So energy correction, if not done right, can result in things. For example, if you put an asymmetric low energy window that is barely covering the main energy that we care about, you get something like this, or a high energy window that, again, doesn't show the things we care about, you get this. But once you put a symmetric energy window, you get the thing that we want. Here's an example of non-linearity correction. Remember those things where the edges of the PMTs are different and the center of the PMTs? If you don't do linearity correction, you're going to get these weird stuff here. Here's an example where people have done linearity correction, energy correction, but they did not do that third step, which was to do uniformity correction. Okay, so still you got issues. Cracked crystals you're going to see. You want to fix this, otherwise you're going to start thinking of this as defects in the human body, such as in this scan. This was a faulty PMT. The technologists had not caught it, so they would find this only later probably. And then you've got a patient that is being scanned and you're seeing some artifacts here, and you know that could be totally confusing the diagnosis, whereas it was really had nothing to do with the patient, had everything to do with the scanner. The bar phantom, if you don't place it exactly parallel and perpendicular in the right way, you're going to get aliasing sort of artifacts. Okay. And also in tomography, because you're rotating the camera, if the camera is not properly rotating and it's not centered at the center of the image, the reconstruction is going to get all messed up, and because it's the center of your rotation is not the center of the image, and things are being confused here. Any questions so far?
No.
Okay, so let's talk about tomography. Tomography is very exciting, honestly. It's just mind-blowing how tomography actually works. Like today's, medical imaging works based on tomography. The idea is you're going to penetrate into the patient without actually breaking the patient's body open, right? So tomography comes from the Greek tomos, means to slice or section, and grapho, which is to write. So you're writing or you're creating slices of images through your patient without actually slicing your patient. By producing sliced images, tomography has the effect of eliminating blurring. Otherwise, you're getting a projection, and so all the layers of your body are adding together to give you a signal. So you get a 2D planar projection, but that has significant blurring because you're not resolving the different planes. And that's, of course, going to give you better contrast and localization. You know where the tumor is, you know where the myocardial, defect is, perfusion defect is, etc. There are many different types of tomography, depending on what is used. Is it waves that are being used to image or particles that are being used to image? And also their origin, whether, for example, the waves, the signals coming from inside the body or outside the body, which we've alluded to before. So we already mentioned these before. We mentioned scintigraphy is analogous to X-ray radiography. And when you go to planar, we showed this before, and you're rotating around when you go from planar to tomography, when you're rotating around the subject, if the source is X-ray, transmission X-ray, we call that CT. If the source is emissions coming from inside the body, gamma rays, then we call that SPECT and PET image. Now, people often think that CT, X-ray tomography came before nuclear medicine tomography, but that's actually not true. It's quite impressive that in 1963, well over a decade before, or 9 years before the first CT scanner was publicly announced, 1972. In 1963, David Cole and Roy Edwards, they invented tomography in emission tomography. So this is a patient who's been injected with radioactivity, I suppose. So this is early 60s here. And they said, well, we got detectors, let's rotate the detectors around the patient. Now, back then, they didn't know how best to reconstruct. So they did the simplest imaginable reconstruction, which is back projection. It's not the best. It's going to be quite blurred. It's not as good as filter back projection, but it's it works to some extent. So they did it. They invented this, but I don't think people took much notice. So actually, emission tomography, nuclear medicine tomography, showed up before CT did. But CT really ended up having more popularity early on. Sir Godfrey Hounsfield, of course, invented this. He was sort of in this research arm of the EMI. EMI was the company associated with the Beatles, for example, amongst many other records. And they had some funds, allocated for research. So he thought of this idea in 1967, took him 5 years to publicly announce it. Initial estimate was that the whole entire world may need maybe about 25 of these machines. And of course, that has changed. So he had this idea that you could determine what's inside a box by taking X-rays at all angles around it, which is tomography. You shine X-rays through it. You don't know where in the box the attenuation is occurring if you just look at one direction. But once you go around all directions, you're going to be able to resolve it using tomographic reconstruction, for example. So he called this computed tomography, right? And turns out there was this other guy, Alan Cormack. He sort of had similar ideas, and he wrote, I think, a couple of papers sort of saying this. But nobody really took notice of it. He kind of developed the idea, moved on to other things. And turns out, decades earlier, this guy called Radon had also conceived of these ideas. Anyhow, so Hounsfield develops this, and then people realize, oh, Cormack is also saying the same thing along the same time. But then again, Radon had also thought of these decades earlier. Therefore, we call the projection operation the Radon transform. When you take an image and sum it all along rays to see what the X-ray image or the gamma ray image looks like. But these two individuals won the Nobel Prize in 1979. And yeah, so there's some prototype where, studies on preserved human brain, then on fresh cow brain from a butcher shop, and later he also imaged himself. And these are the kind of images they were originally getting. Scanning time was 9 days on some of these samples. Reconstruction was many hours, or at least a couple hours here. They were printing images. Resolutions were not so great, but and then when this was constructed, it took about 4 minutes. Ultimately, at about 7 minutes per picture when they built the actual clinical prototype, I think in 1972 or soon after he announced it. And they had to do stuff in there, like they had to have a water tank because they had a big dynamic range, like from parts of the brain, because there's smaller intersection with the brain, you would get much less attenuation, whereas here you get much more attenuation. So the range of numbers they would get on detectors were very different. So the detectors couldn't handle so much difference, so much dynamic range. So they actually use a water tank to kind of make everything almost equal in terms of amount of transmission. We don't do this, of course. Nowadays, detectors are much better. They can handle these differences in the range of numbers that we get much better. Okay, so the first patient brain scan was made in 1972. And of course, to commemorate him, and by the way, whole body scan in 1975, to commemorate him, the Hounsfield units are used. And I know you know about like the water, the number is 0, Hounsfield units, but air, bone, etc., etc. So back to, and I don't want to say forward to, but back to, because emission tomography was actually constructed in 1963, as we saw. But then later, this was revisited in the 70s and 80s, probably energized by the role of CT, because there's always interactions between the scientific disciplines, right? So people started taking this quite more seriously, rotating the gamma camera around the patient, as you can sort of see here, and using image reconstruction. So you could have a single head rotating around the patient, or dual heads rotating around the patient, or could even have triple heads, like 1, 2, 3 rotating around the patient. So the 2D planar images get the projection data and the camera is rotated, and image reconstruction can be done either using so-called filter back projection, which is a pretty good technique, or iterative image reconstruction, which is even better. And nowadays people are talking about artificial intelligence-based recons that assist these methods. So this is a projection of the patient. We call this a 2D planar image at a particular angle, so therefore a projection, and then a line of pixels along this particular projection, we call that a profile. So there's a profile through the patient. And remember, we're going to be rotating around this patient. So how do we utilize and measure projection data at various angles to generate 3D images? That's the question. I got a whole bunch of his intuition, and their intuition was, if you rotate around the patient, you know what's going on inside the box. Well, how do you actually do it? And that is the beautiful field of tomographic image reconstruction. Okay. So there are a number of approaches to image recon. There are analytic techniques. You might have heard these in the world of CT also, and there's iterative techniques. So the world of CT is only in recent years really coming to iterative techniques. It used to really be focused almost purely on filter back projection in clinical routine. But in our world, the world of nuclear medicine imaging, we switched quite a while ago, long time ago actually, to iterative methods. One reason was because the signal in nuclear medicine imaging is coming from inside the body, we cannot be injecting too much into our patients. Therefore, the images can be noisier. Unlike CT, where you suddenly give it a massive dose or a relatively large dose, and then you stop. You cannot do that in our field. It's already inside your body. You can't stop that radiation. So you gotta give it a limited amount. So we have been dealing in nuclear medicine with noisy images, and we just knew that we have to switch to iterative methods. And then the world of CT initially, they were like, well, this is already good enough. But now they're thinking, well, why? Why can't we just inject our patients, or sorry, in the world of CT, why can't we just giving them much less doses? Because the public's mind has been activated. They're like, why are you dosing us too much? Can you not dose us less, et cetera, et cetera? The answer is, yeah, if you do iterative recon, you can actually achieve very good images. And nowadays, people talk about AI-driven, AI-based, artificial intelligence-based recon, that you could get significantly less injected radioactivity in our field, and also inject, beam doses to patients in CT, and get very high-quality images. So we got analytic methods, and we got iterative methods. Now, iterative methods, a big part of that is statistical methods. I just want to mention, though, that not all iterative methods are statistical. Statistical means that you understand the noise pattern and structure. You take that into account. There are some other methods, like algebraic methods, that are iterative. They go in a loop, but they're not smart enough to think in terms of the nature of noise. They're like, I'm just going to solve this. I don't want to think about this is Gaussian noise, Poisson noise. I don't care. I'm just going to solve this. So that's why I think iterative statistical recon methods are in what we're presenting here, have demonstrated added value. So simple back projection. Remember that original device that was built in emission tomography? Simple back projection. So how does it work? All you do is, as you're rotating around your patient, imagine you got a point source. This point source is going to show in this projection here, in this one here, here. All you do is you back project all these from all these angles. When you back project, you're going to get this. This is a reconstructed point source. Notice how it's blurred, because you're really, there's a lot of uncertainty. You're back projecting. There's a lot of signal here that is in the wrong place. You're not doing any filtering. So you end up with something that is like blurred. Here's an example. This is the original image. If you do only two projections, let's say along this direction and along this direction, and you back project them, this is the image you're going to get. Terrible image. If you do along 4 angles, this is the image you get. 8, 16, 32. So this may look good to you, but it's really not that good when you think about it. The contrast is not great. You have all this kind of spill out, if you want to call it. Of course, the more projection angles, the better the image, but the image still, even at this angle, at this so many angles, 32, 64, 120, it's going to be blurred. So filter back projection, and let's not talk about filtering, what it means yet, but it does stuff to it, which is informed, which is very intelligent. And you actually end up with this. Look how filter back projection is much better than non-filtered back projection. Just simple back projection. See how blurred it is, as we were showing before. Before we were showing for 32, but even 128 angles, it does not look great. Whereas with filter back projection, sure, you see a little bit of artifacts here and there, but it's much, much better than this. So there's this magic filter that gives you much better images. Here's another example of an example of a patient, and you're doing back projection image, looks awful. Filter back projection looks quite better. So yeah, back projection, you just back project everything. But again, the signal is not filtered, it's messy. Filter back projection says, no, I'm not going to back project this. I'm first going to do some weird filtering, which is informed, intelligent. There's a lot of beautiful math behind this. And then I'm going to back project. Now, this looks weird. Like, why would you ever do that? But it turns out mathematically, that's a good idea. So just to give you an example, you've got a box of numbers. Imagine this is your patient, a 3x3 grid. You forward project this patient, you get a total of 18 counts here. Forward project 14 counts, forward project 1. Forward project 9, 15, 9. From these two sets of numbers, imagine like 2 angles of projection X-rays, for example. You want to, or emission scans, gamma scans. You want to reconstruct this. If you back project these numbers, the 18 gets equally split between these, 14 gets equally split, 1 equally split. Same with these 3. You add them up, these are the images you get. So, sorry, what was it? Yeah, this is the original image. This is the new image you get by adding all these. Doesn't look that great. This 6 has become 4.8. But if we do this filtering step first, then back project, filtering step, then back project, these are the numbers we're going to get. Look how the center, which the correct value, the true value being 6, in back projection, it became 4.8, but here in back projection is 5.6, which is quite closer to 6, so it's better. So what is this magic filter? Turns out because of some clever math that if you convolute, right, that is simply add and multiply together each data point in a projection with this sync looking function, which looks like this. We first convolute these profiles and then back project them. It turns out mathematically you can show that in a perfect scenario, you're going to get the original image back. Okay, so there's a bit of what does this thing even mean? What is this sync filter that you have to do? This takes us to the domain of frequency domain, a strange, bizarre domain, lovely domain, you know, Fourier transforms you might have heard of. Mr. Fourier, initially when he said this, people couldn't believe what he was talking about. But basically, you can represent any signal, any image in 1D, 2D, 3D in a frequency transform or domain. The center of this represents zero frequencies. Zero frequency means you've got like a DC offset, like a constant. And as you get away from the center, this represents how much sinusoidal behavior of increasing frequencies you have. So if you've got an image that has a lot of edges and a lot of, you know, quick movements in it, like sharp changes, you're going to get higher and higher frequency content as you move outside from this ring. But if you get a really constant image, a boring image with not much massive changes, you're going to get a lot of concentration in the center and not much going on at the edges. So the process to transform an image into its equivalent sinusoidal frequency content is called a Fourier transform. So it turns out any image can be represented by a summation of a whole bunch of sinusoidal curves, which was a strange discovery by Fourier. Okay. Then it turns out, just hang in there. This is probably the most difficult part of what I'm saying today. If you've got this thing, this sync function that mathematically you can show, you have to convolute your image with before you back project. Turns out in the frequency domain, it looks like this. So this signal, the frequency domain has no content at 0, but has a lot of content at a certain frequency. Okay, so we call this, okay, so this is like a ramp filter. You might have heard of the term ramp. So the ideal filter in its frequency domain looks like a ramp. Okay. Now this ramp has a number of roles. Look how it's basically saying, I'm going to really emphasize, add, aggregate to the higher frequency content than the lower frequency content. It has an intuition. It says, in the projection operation, your device has been receiving these projections and killing high frequency content, like lowering their impact, because you're projecting. It's like saying, hey, you're projecting, you're killing me here. Let me help you. Let me amplify. Let me undo some of the harm that this projection has done and bring up some of the frequency content. So you try to bring up some of the frequency content. So, okay, so imagine this is your imaging data, but this is in the frequency domain. Like, how much frequency content does your imaging data have? Imagine that the this is what you've actually measured in the projection operation, but the ramp filter says no. Take your signal and actually multiply it by me, so I give you higher content in these frequencies. These are the mid-range frequencies. The really high-range frequencies tend to correspond to like things like noise, but the mid-range frequencies are real content. This is how the body looks. It has mid-range frequencies. It's not just some boring, flat structure. The body has some frequency content. And when you multiply your signal by this ramp filter, it brings out the best. It brings out the truth in it. Okay, so the high-frequency component, the really high-frequency component, can contain mainly noise. The low frequency content is the blaring due to the projections. What we really want to emphasize is and amplify is the mid-frequency, mid-range frequencies, okay? And the shape of the filter itself can be changed. There's an ideal filter, but the truth is that this filter does suggest that as you get more and more signal here, I'm going to amplify it more and more, but you don't really want that because this stuff here is noise. So you may want to even cut this part of the ramp and say, you know what, you're going out of your way too much. My image is noisy. You're kind of clueless about the fact that my image is noisy. Don't amplify this part too much. Amplify this much more. So that's why people switch from a ramp filter, which is great. Theoretically, it's best if you have a noise-free image, but we do have noisy images to begin with, and therefore it can really amplify high frequency noise. To modified versions of the ramp, right? Things like other kind of filters that kind of amplify the mid-range. So ramp looks like this, but we end up with other things like we were just showing the Butterworth, different kinds of Butterworth, Hamming, Parson, different kind of filters that kind of amplify the mid-range frequencies. Because we don't want to amplify the noise. Okay, and if the ramp filter allows frequencies above the maximum which are resolvable by the imaging system, you could even get aliasing stuff. So you really don't want filters that really allow too high frequency content because they're going to create these aliasing artifacts. So here are some examples of reconstructions. This is reconstruction using a ramp filter. This is Shep Logan. So exactly. So as you bring down the Shep Logan in a sense, or you have a cutoff frequency, you start to not amplify high frequency signal. Therefore, you're going to get less noisy images. But because you're kind of limiting frequencies which you're amplifying, you also do get limited resolution. Remember how today we were talking about resolution versus sensitivity trade-off? You cannot win on both sometimes when you're just playing with a parameter. Here, you're changing the filter. The filter is giving you less and less noise because it's having a high cutoff. It's removing the high frequency amplification. But it does give you more and more blurred images too. So it really depends on the application, which one you prefer. There's a classic resolution versus noise trade-off. Which one's the best? Depends on the anatomy, depends on the patient, depends on what your observer preferences, depends on the task, really depends on the task. Same thing with when you post-filter the image. Let's say you already reconstructed an image. You could still filter it with like a Gaussian filter. So here, these are all ramp reconstructions, but you could be post-filtering the images. Notice how as you increase the 3D Gaussian width from 2 millimeter to 4 millimeter, 6 millimeter, 8 millimeter. This is actually something I'm doing right now as a physicist. We're having a very interesting study, brain imaging study, multiple centers, study of the effect of vascular disease actually on brain function, which is quite interesting and fascinating. And we're having multiple sites, and I have to play with these post-filtering numbers. So when I increase these numbers, I get images that are blurry, but they have less noise. So which one do I pick? So I'm playing with this, and I'm trying to make it more consistent between the different sites. So true or false? Help me out here. Ramp filter is applied in the frequency domain and allows mid and high frequencies through, and is used in filter back projection as part of the reconstruction, whereas Gaussian filter can be applied to the final reconstructed image and allows low frequencies through in order to reduce the noise. Is this collective statement true or false? So that ramp filter is something you do during reconstruction, whereas Gaussian filtering is something you do after reconstruction. Any thoughts? Anybody? In the words of Lion King's son, somebody, anybody.
Is it true?
It's true. Thank you for that. Yeah, so it's true. So ramp filter happens during reconstruction, Gaussian is after it, and ramp filter is there to amplify mid and high frequencies. But if you don't really cut it off at high frequencies, it does amplify noise. So you could post filter, or you could change the filter itself. So you could do a combination of these, basically. Aliasing is this weird phenomena, sometimes hard to explain, that of course this is the same building. It's just that the camera being used, you know, old TV systems, you would see aliasing in them a lot. This is the same building. It's just that the camera that is being used its resolution interferes with these really high frequency content of the image and might create weird patterns, as you can see here. Imagine you've got this, these are the bricks. Think of this as the bricks that you're in this object. This is a frequency content. And if you have a resolution that is better than the size of the bricks, meaning smaller, meaning finer, you're going to be able to resolve them. But imagine that you were only able to resolve resolutions from here to here to here to here, which is not as fine as, I should really say, half the brick size. Imagine this is the brick size. From here to here is the size of a brick. If your resolution is not better than half, you're gonna sample this one here, this one's gonna sample it here, this one's gonna sample it here. You're gonna think and imagine that you have a signal like this, a high wavelength, low frequency. You see these weird things here happening? They look much, much longer in wavelength compared to the size of the bricks. And this is this weird impression that the human eye forms. So aliasing is the appearance of high frequency components as low frequency variations. You have high frequency stuff, but you start seeing these low frequency variations. The theory says, the sampling theory says, if you sample your frequency content at better than half of its length, you're good. So if you get the smallest cycle length, it has to be or the brick size. If you sample at half the brick size, you're good, half or better. But if you sample at worse than half the brick size, half the wavelength, you're going to get these weird low frequency variations that are purely artifacts. So you need to be sampling at least at 2 points per cycle, the highest frequency content that you have. Now there's a practical rule of thumb. Here we thought about full width at half maximum, the repetition patterns. But we also like to think of the full width at half maximum resolution of a scanner. Like if I have a point source, how big is the point going to look? Typically, you know, in SPECT, we've seen 1 centimeter. In PET, we've seen like half a centimeter. For practical purposes, this rule translates to the fact that you need to be sampling at around 1/3 of your resolution. I mean, technically, even half is okay, but 1/3 is a safer one. So imagine if you have a PET scanner that has a resolution of 6 millimeters. Sorry. If you have an object that you want to resolve down to 6 millimeters, your detectors in PET, for example, should be about 1/3 of that, 2 millimeters. So if you have about 2 millimeters, you're going to be able to resolve 6, maybe 4. Like it depends whether you take this rule of thumb to be 1/3 or 1/2, give or take. And if you don't, you're going to get aliasing artifacts, right? So for example, here's a sampling that is happening that is really poor, 1.6 centimeters. You're going to start seeing aliasing. You get loss of resolution and aliasing. So you want to be careful about it. It depends on the resolution of the object that you want to resolve anyways. So here's a question for you. How much should a single head camera system rotate around the object or the subject to have full tomographic coverage? If I'm a patient and you want to go around me to do tomography, how much are you supposed to rotate around me in order to allow full tomographic coverage and therefore resolving my body? What do you think it is? 90 degrees, 180, 270, or all the way 360? What's your guess?
I would have thought 360.
Right, and that's what I would have thought too. But turns out, Ali, that is actually half of that here. Why? Because the same signal that is going to the back of you, the same signal can be coming to the front of you. Meaning, so the answer is actually 180. The reason is because you're having a projection, whether you're summing this way or you're summing that way, the sum is the same. Okay. So, you know what I mean? Now, of course, attenuation changes that, but put that aside for a moment. Imagine there's no attenuation. Imagine you're just summing counts. Whether you're here or at the back of me, you're looking at the same thing. You're looking at just these lines that are passing through me. So it turns out to be 180 degrees. And look, if you do less than 180 degrees, you're going to get terrible images, right? As you increase the amount of coverage of the body that you have, you're going to get better and better and better images. Now, of course, you could do 362 because of a number of other reasons. Remember how I said the closer that you're to the detector, the better? Well, that's when these things enter the picture. If I really care about the front of my body more than the back of my body for imaging, sure, then stay here. But if you want to resolve the whole body, front and back, and you only do imaging at the front, you're going to get poor resolution at the back of my body because it's too far away from my collimators. So in that case, it's actually better for you to do a whole 360 coverage, so you don't have this resolution degradation. Same thing for attenuation. If you're close to here, you're going to be seeing less attenuation from stuff here, but you're going to see more attenuation from the stuff at the back. Therefore, you're going to have a significant loss of signal, possibly. So again, you don't have to cover 360 degrees, but if you care about full coverage, you can. But if you're looking at the heart, for example, if you really want to focus on the heart, then you can just stay around here. You don't have to go from the back because you're closer to the heart this way. So it depends on the application. And if less angles are sampled, for example, or the object's not fully covered, you're going to see all kinds of artifacts. Angular sampling, how many angles? Like, sure, I got to go around you 180 degrees, but how many angles? There's a formula for it that people use. We won't go through that, but you know, there's a formula. And so this formula is, however, for filter back type sort of reconstruction, for iterative recon, and also nowadays with artificial intelligence driven, all these things are starting to change because, you know, some of these proofs don't work that way, or, you know, the concepts are different. So just as a practical example, this is, I want you to feel this, make it more tangible. Imagine you have a tomographic PET or SPECT system that has a full width half maximum of 6 mm resolution. Imagine the field of view. How much is the field of view that it images? Like, just think 2D coverage is about, you know, the diameter of the field of view is 40 centimeters. How much is the minimum required sampling interval? Like, what should be the detector size, and how many times should you, or at how many angles should be going around the patient? Okay, so the rule of thumb said the sampling should be about 1/3 of the resolution. So that gives me 2 mm. So the detector size should be 2 mm. And then this means if the field of view is 400 mm, you're going to have 200 samples. So you're supposed to be having 200 detectors, for example, to cover 40 centimeters. And if you put it inside this formula for the number of angles that you need, it turns out to give you about 300. So you need to be rotating 300 times, ideally, to achieve such a thing. Now let's move on to statistical iterative reconstruction. Statistical iterative reconstruction has three really great things about it. You don't have to assume that what passes through your body is a perfect line. Because in fact, when you enter crystals and detectors, there could be some blaring that happens, scattering inside the crystal. Nothing is perfect. You could model those. You could model blaring happening in the detection process. Also, filter back projection really doesn't assume any noise model or a very simplistic Gaussian noise model, whereas noise is Poisson, actually. There's this noise that detectors measure. It's called Poisson noise. It's not Gaussian noise. And so we can actually model that in image reconstruction. Finally, filter back projection type algorithms assume you have an infinite number of angles around the patient. And you have a lot of them, but you don't have to have a lot of them. Sometimes you don't have a lot of them. And none of these need to be assumed to be able to do this. So I won't go through the details, but basically iterative recon, also in the world of CT recon, similarly, works like this. You start with an initial image. You say, if this is the truth, what do I expect to get in the projections? What kind of detection do I expect to measure? So you have to have a forward model, like a radon transform, something that says, if this is a truth, this is how much signal you're going to get in your detectors. Then you compare that with the actual measured projection value, actual measured, detector values. You compare them and calculate some kind of a ratio or a difference, for example, between them as a measure of error. Then you back project it, you come back to the image space and you've calculated some kind of a correction image that says, look, these two are not that close to each other. I'm not impressed. I'm providing you with a correction. Now correct your initial guess. Give me a better guess. And then you improve your guess. Then you again keep doing this. You say, okay, this is my new guess. And you're going to say, fine, I'm going to give you another chance, another iteration. What would this image look like in the projection space, in the detection space? How does it compare with what I actually measure? Oh, it's still not there yet. Let's do a correction, so on and so forth. And so with more and more iterations, you get better and better images. And iterative reconstruction, I would say, tends to do better than analytic recon. I would say if you were plotting bias versus noise for the same bias and deviation from the truth, you would get less noise in iterative methods. So gradually in our field and increasingly in other fields, people are switching to iterative statistical methods. So as a summary, they can incorporate things like attenuation and scatter and resolution in the detectors quite better. The MLEM algorithm is very well known, does very well, models the Poisson noise. It's called the maximum likelihood expectation maximization. It was introduced in 1982, and it's really used very routinely nowadays. You may get streak artifacts in filter back projection, but they're not seen with iterative techniques. There is some non-linearities with OSCM because unlike filter back projection, which is kind of linear, this one is not. But for just I don't want to oversimplify, but I might. I mean, they tend to be better. Of course, you have to know some of the artifacts that they may produce, like iterative recons, but they're pretty good. Last part of my talk today is focusing on SPECT concepts and designs. So again, in SPECT, you have single photon emission computed tomography. You rotate it around the patient. So you have an X and a Y coordinates inside the detector. Sorry, so imagine you've got this detector. It's got an X and Y goes inside, X and Y, and you rotate it at different angles, right? And then you get those data, the X and Y coordinate values at different angles, and somehow using image reconstruction, you convert that to reconstructed 3D images of the patients. Of course, cardiac data can be reoriented, et cetera, et cetera. We won't go through those details. But commercial SPECT systems have been typically based on the gamma camera, again, using 1 or 2 or 3 heads. Here's an example of 2 heads, and you would be rotating around the patient. This is an oversimplified example where you rotate only 4 times with the 2 heads. In practice, of course, it's many, many more steps. So here's an example of the 2 heads rotating around the patient. The patient's fixed on the bed, but the camera is rotating around the patient. High angular sampling, step and shoot, or you could do continuous, but step and shoot is more popular, more common. 2D planar images are created. Again, this is the X and Y coordinates. You create these 2D planar images, but you rotate them. I won't go through I'll send you the notes. You can look at some examples, somebody giving a tour, I think, of facilities, etc. And in our YouTube videos, we go through these in a lot more detail. Image reconstruction is available by filter back projection or iterative recon. We already talked about that. The spatial resolution has a concern, as we've mentioned multiple times. As you get farther away from the collimator, you get poorer resolution. Okay? So what are the implications of that? The implication is that obviously the resolution is worse, so you cannot resolve these 2 points, whereas you can. So to do that, we have to play with certain things. And this all depends on a whole bunch of designs. But at the end of the day, given the system that you already have, you could try to rotate this around the patient in a contoured orbit, not a circular orbit. So you can bring it closer to the patient. So contouring the patient in this way, so you get closer to the chest, for example, as opposed to having a circular distance pathway. And also, there's a question of what kind of reconstruction-based improvements can we do? Because again, there's attenuation happening in the body, scattering happening in the body, blaring happening in the crystals. What can we do to correct for this? So these are something we're going to talk about next time in the next lecture. There are a number of novel SPECT systems, some that move beyond sodium iodide scintillators to more expensive but better detectors, so-called semiconductor detectors, CZT or CZT. And so let's quickly talk about that and some novel designs and geometries, which chapter 4 of our text talks about. So basically, when you switch to semiconductor or solid state detectors, you end up with better energy resolution, okay? So the resolution can actually improve significantly, right? I mean, here's one example, but it can improve even more. Also, you can actually get less bulky material. They're more expensive, but they're less bulky. And they're not sensitive to humidity, right? And at the end of the day, you can have higher attenuation, therefore higher stopping power, so more sensitivity. Okay, so you get better resolution and better sensitivity. This is an example where it's a win-win. There's no trade-off between resolution and sensitivity because you're changing your material. You're changing your material, which has better resolution and sensitivity. But again, it's more expensive, so historically, it's taken a while to transition towards this, but increasingly this has been happening. So again, looking at the numbers, look at sodium iodide, the effective Z is 51, okay? That part is the same as, let's say, in this example of a CZT or CZT, but the density here is less than the density we're having here. So because of the higher density, you're going to get better sensitivity for solid state detectors, just to show you an example. Multi-pinhole, I already showed this before, where you could be using pinholes to get really, now this system, you no longer need to rotate the entire camera. It's just that these pinhole collimators do rotate. So you don't physically see it, but inside the camera, they're rotating. So it allows less mechanical movement. It's a very innovative way of looking at it. Actually, I take that back. These ones don't rotate. Sorry, I take that back. These ones don't rotate. These ones can already resolve, which is even more amazing. But in this design, you're having these things where you've got these upright positions. These ones are rotating. These ones are rotating. So again, the system is not rotating, but what's inside the system is rotating. Whereas here, because you're having pinholes, it turns out you're sampling at so many angles, you don't even need to be rotating these. So it's a stationary, very impressive stationary camera. Which is kind of like what the PET world does naturally, but for a SPECT world to be able to build a stationary camera, it's been very impressive. There's also, you have things that are conventional rotating gamma camera designs, but because they're dedicated cardiac imaging, they kind of change certain things about the collimators. So they moved, instead of a parallel hole collimators, more to converging. But it's not converging everywhere. It's only converging towards the heart, but parallel elsewhere. So it's a very strange design in a good way. Notice how it's parallel here, but as you get closer to the heart, it becomes converging. So I can't really call this a converging collimator, but parts of it are converging. Okay, so parts of it are converging, and in a funny way, these ones are diverging. So collectively, it's covering the same field of view, but it puts more emphasis on the sampling at the center than at the away from the, or if the heart is centered, it puts more emphasis on the heart sampling and else outside. It's a mix of things. So it's kind of an innovative design. Or you could have the patient sit on a chair. You can see here, and you could be rotating, right? So if you have a chair, and I saw this many years ago, I was visiting a center, they had a very conventional planar camera. They said, well, okay, I cannot rotate this around my patient. Well, why don't I rotate the patient? So there's all these designs. So this is kind of actually doing, it's a triple head. Instead of the system rotating, you could have the chair, for example, rotating. Okay? And you could have X-ray sources for attenuation, correction, etc., which we'll talk about more next time. Okay, so I'll stop here because next time we'll talk more about quantitative aspects, how to generate quantitative SPECT images. Also, let's talk a lot more about PET imaging, and also let's talk a lot more about radiopharmaceutical therapy, which is very, very exciting. Okay, I'll stop here. Any questions? Okay,
Thanks so much.
thank you very much. And if you have any questions, let me know, and I can send you. I'll send to Ali, to the other Ali. I'll send her the PowerPoint or the PDF for the PowerPoint, so you would be able to all look at it. Okay.
That's great. Thank you.
Yeah.
Thank you.
Thank you. Have a great day. Bye.
Thank you.
So welcome to this session, continuing our discussion on the physics of nuclear medicine. We sort of covered we covered the introductory aspects to nuclear medicine, to tomography, to how imaging is done, quality assurance. And in SPECT, we looked at concept and designs, but we want to wrap that up with quantitative SPECT and how that's done, and then move on to PET, and finally to nuclear medicine therapy. So SPECT has been thought for years not to be quantitative, which is not true. Okay, so let's clarify that misunderstanding. It's no longer true. But let me explain why people thought for a long time that SPECT is not quantitative, and why, in fact, it was not quantitative until people managed to fix it. So one key issue was attenuation in SPECT. For example, in the human head with technetium-99m, around the attenuation, the average attenuation factor is 2.5, increasing to a factor of roughly 5, meaning, when it's 5, 1 in 5 events only survive. Okay, so it's a factor of 5 attenuation that's happening. You're losing a lot of events, or in this case, you're losing, only 1 out of 2.5 events sort of survives. So something like that. So the point is that when you do filter back projection, attenuation correction was not done, and result in reconstruction errors. And then when you have attenuation in the body, so for example, the radiation is attenuated, let's say through the photoelectric effect, and it's absorbed and it never makes it to the detectors, then if it's especially deeper in the body, that's more likely to happen. So if you actually look at some object deeper, when you do reconstruction, deep within the object or the subject, you're going to see underestimations, right? So these are things that, in fact, even physicians had adapted themselves. So when reading an image, they're like, oh, this thing is because of attenuation, not because of an actual defect, for example. And and the issue is that in the body, we don't have uniform attenuation, so it's not straightforward. But in brain or lower abdomen, you could sort of assume, people sort of used to assume that you had uniform attenuation. So there's this thing called the Chang method that people used to use. It's a software-based method. No special equipment, like no CT or no transmission source was there to calculate the attenuation, but it's an approximation, which sort of assumes uniform attenuation in the body, almost like assuming the body is like all soft tissue, for example. And so they did some kind of multiplication, right? But the problem is that that's inappropriate in non-uniform body. I just keep saying the same thing. For chest imaging, the lung, we've got a serious issue where attenuation is quite less than in other tissue. And so again, with head and abdomen, lower abdomen, it sort of works. But then when we have non-uniform attenuation, there's a way to correct for it. There's two ways to correct for it. One is to use CT, so like an SPECT CT camera, which are increasingly utilized. Or using some kind of a transmission source, almost like a low-cost version of CT, where you have something sort of going around, kind of the same concept as CT, which is what used to be used before CT and Spectra kind of merged together. But again, SPECT CT is becoming the instrumentation of choice for quantitative imaging, because you could do the CT at a very fast time, and you get very reliable numbers. And so you measure the attenuation maps, and then you allow, you use those attenuation maps to to correct for attenuation in the reconstruction of SPECT. Same thing is, by the way, true for PET. We'll get to that later. Also, when you have SPECT and CT, that allows you to do fusion of imaging, like let's say anatometabolic imaging or anatofunctional imaging, depending on what function SPECT is imaging, and anatomy is being measured by CT. So merging has two advantages. You get more quantitative SPECT, and also just from a clinician's perspective, having fused images is valuable. So again, Chang correction method, you sort of assumed, well, I already talked about that using uniform data, but you could also, take the measure attenuation coefficients from CT, for example, and then you could calculate the attenuation correction factors. So this is kind of like a Chang method, but benefiting from the CT data, and you could get quantitative numbers. So instead of CT, you could also use transmission scans. This is what used to be done. And so either there was nothing being done, or there was transmission sources, but then increasingly there's use of CT. So when you have a transmission source, you're basically having this hot rod, for example, like it could be a moving line source, right? Or a stationary line source with converging collimator, as we're sort of having here. This is actually a line if you look at it this way. But again, so you could be, essentially the point is that to expose your object with transmission coming from outside, same concept as CT, and that allows you to measure how much attenuation is happening. So you could also, in the past, especially people, again, when transmission was more and more popular, you could do simultaneous acquisition of transmission emission. You still do, you can. But there's going to be a bit of crossover, because if this is your transmission window, let's say you've got something that, for example, you've got gadolinium 153 at 97, around 100, for example. If you put this energy over that for transmission measurements, and this energy over the technetium 140 kV for emission. But there could be crossover. Like if an event is coming here, but it's scattering in the body, lowering its energy, by the time it arrives at the detector, it might be in this window, and it might confuse things. So there's a lot of work, research on how to deal with these things. So if you have an estimated attenuation map, again, from CT or whatever, you could use the Chang method. The issue here we're having with the Chang method is that it is being based on the, you reconstruct an image and then you correct it. That reconstructed image, the original one itself, is wrong. So you could do iterative Chang, but honestly, people are moving away from this, and Chang is not in the picture too much anymore. People are really converging towards statistical iterative image reconstruction, where you can really model the attenuation factors within the reconstruction. So if you want to remember one thing, is the fact that field of nuclear medicine ahead of the CT world really started to converge on using iterative statistical image reconstruction, giving you truly quantitative reconstructions in both SPECT and PET. So SPECT is now quantitative if you're doing CT or transmission to measure attenuation. And then the CT world, of course, has arrived on the scene doing increasingly more iterative reconstruction. But nuclear medicine was ahead of the CT world in doing this. And partly, as I mentioned last time, this was because nuclear medicine were limited in count, and therefore you're getting noisy images, and you felt the urgency to use image reconstruction that in an iterative statistical way, and the results were great. So again, people used to do nothing. Some doctors to this day just are used to looking at non-attenuation corrected images and just sort of figuring out if this is an artifact of the recon or if this is a real defect, let's say myocardial perfusion defect. But then Chang came in, and then iterative Chang, but really the best approach is statistical iterative reconstruction. Of course, nowadays people are also looking at incorporating AI-based methods, artificial intelligence-based methods, as the next generation of techniques. So statistical iterative reconstruction, the concept is that you have some image. Let's assume you know the truth. If you know the truth, using the so-called system matrix, which models the relationship between the image space and the projection space, you can calculate what the projection space is. And then you can sort of model the fact that there is noise being added to it, like Poisson noise. So if you have such a system, you can actually, within the system matrix, model how much attenuation is happening, because your CT gives you how much attenuation is happening. So you could actually build this, and then when you do reconstruction based on this formalism, you could model that. So here are examples of rest and stress myocardial perfusion studies, and with no correction, you get these kind of things. For a normal patient, you see some kind of artifacts, but this is not a real artifact. This is not a real defect. This is an artifact. Whereas once you do attenuation correction, you get these images. So we talked about, again, no correction. You see this sort of drop dip in the middle. After you do attenuation correction, something funny or bizarre happens. And people initially were like, look, we told you not to do attenuation correction, because once you do attenuation correction, instead of a dip, you know, almost have a, like a, you kind of have a upward trend, okay? So they're like, oh, something's wrong here. Why isn't this flat? Well, guess what? Sometimes when you correct for a big issue, the smaller issues start to show up. This is now another issue. You have taken care of attenuation, but another issue shows up, and that's the issue of scattering. Attenuation is when you lose events, and the event that was intended to be detected at a detector was never detected. But if in the meanwhile, you also have scattering, and the event is being scattered but being detected in the wrong place. Now, some of the detectors are detecting more things than they would have because scattering is moving in that direction. So you need to then correct for a scatter. Well, and once you do that, you get this nice flat distribution. There's other things like resolution recovery that makes images sometimes look smoother and even sharper, but then they might give you some edge artifacts. But essentially, there's all these corrections people work on. And so we've gone from having an image like this, which doesn't look good at all, to images like this and that, which look quite better. So scatter correction, there is a simple method to do scatter correction, and that is by putting a lower energy window to actually measure how much scattering is happening, because those are the lower energy events that are coming here. And when you measure how much scattering is happening here, you can sort of extrapolate about how much scattering, because here you don't know. Here you're receiving a bunch of events. Some of them are real events, some of them are scattered events. Which one is which, we don't know. But if you put an energy window here, you kind of have an estimate of how much stuff is here. You kind of, using mathematics or interpolation or extrapolation, you kind of calculate how much of this would be here. And then you would subtract this amount from that to get the true images. Or you could use triple energy method. When you put an energy window below your photo peak window and above it, and then you do average in between what you measure here and here to estimate how much scattering is happening there, and then you subtract. And then there's other advanced methods like advanced modeling using Klein-Nishino formula, et cetera, et cetera. And so there are other methods, and you start with an initial image estimate, you estimate the scatter based on that, then you correct for it, et cetera, et cetera. It's kind of analogous to iterative Chang. You start with something, based on that, you know, you get a new image update, and based on that, you keep updating yourself. So I again want to emphasize, SPECT was considered for a long time not to be quantitative, but increasing use of statistical iterative recon with improved modeling of attenuation as well as scatter has really made it much more quantitative. There are other things you could model, like collimator detector blaring, like let's say the collimator or scattering or entering the detector, but then scattering to the nearby detector. You can actually model these things, resolution recovery or resolution blaring. That ends up giving you typically sharper looking images, which can be advantageous for certain applications. So again, example of just good old filter back projection with no correction. Filter back projection with Chang attenuation correction. And then you switch to iterative statistical methods, the so-called ordered subset expectation maximization method. And the images you see, and then you add attenuation correction, and then you add resolution recovery, and then finally you add scatter correction. You see gradually the images have gotten better and better. They look, they tend to be sharper and less blurry. Just overall, you know, there's been tremendous improvements in the quality and quantitative accuracy of SPECT and PET images. So images have become more quantitative. So you could assume SPECT is quantitative if you're doing proper corrections. Okay, so let's move on to PET. Please stop me if you have any questions. Let's move on to PET. So what is PET? Stands for positron emission tomography. Is a functional and molecular imaging technique in which radiopharmaceuticals that emit positrons are visualized. All right, and it allows you to quantify them too. It's not just about looking at pretty pictures. You can get numbers, so you can actually quantify these, biochemical and physiological processes in vivo. It's extremely powerful. You can quantify physiological, biochemical, molecular phenomena with exquisite sensitivity. Okay, like picomolar sensitivity, for example. Originally, PET was used for as a research tool in the brain, but then it took very important clinical role. There was significant subsequent clinical use in oncology, but PET is of course used in other frameworks too, for cardiovascular imaging and brain imaging. The most widely used So just to comment here, originally it was brain research, but now it has clinical brain applications too, right? So let's say for amyloid imaging in Alzheimer's disease. But the most widely used radiopharmaceutical or radiotracer, the reason we say radiotracer is because you use small amounts of it for imaging. When you're doing therapy, as we'll see later, then the word radiotracer is not appropriate. It's radiopharmaceutical. So I myself tend to increasingly just say radiopharmaceutical. The most widely used radiopharmaceutical is, or radiotracer is fluorodeoxyglucose, labeled with fluorine 18. Has similar metabolic pathway as glucose in vivo, except that it's not metabolized further down the chain. We'll see this in a second. But is trapped within tissue and it accumulates. That's why you can see tumor, increased metabolism, increased metabolic activity that is created by tumors. So this phenomena is of interest to oncology, but also because proliferating cancer cells depict increased rates of glucose metabolism, as you know, but there's other applications to it too. But here's an example. You're having a subject injected. You wait for, let's say, 60 minutes typically in the clinic, then you do imaging. You can sort of see that because of this trapping mechanism. So this is fluorodeoxyglucose in, like, sometimes I call it radio-labeled sugar, which is not precise, but it just gives you a picture of things. Fluorodeoxyglucose in plasma enters the intracellular space. This is an oversimplified model. There's more compartments, but you can sort of think of it as intracellular space. And then finally, there's a phosphorylation that happens by hexokinase. And when phosphorylation happens, then you have fluorodeoxyglucose 6-phosphate, and it gets trapped here. It can no longer undergo metabolism or diffuse out of cell. It gets trapped here. And that's kind of nice, actually, because it accumulates, for example, in tumors, and you can sort of visualize it. But again, the only application of FDG is not oncology, though it's the workhorse of PET is in this space, but there's so many other things happening: inflammation, infection, etc. Apart from its, just quotation here, apart from its heavy use in oncology, PET-CT is widely used in a variety of non-oncologic conditions, interconnecting to such disciplines as general internal medicine, infectious diseases, we sort of said that here, cardiology, neurology, surgery, traumatology, etc. Many, 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 many frontiers. And again, PET allows you to quantify phenomena and processes. For example, you could consider looking at assessment of response to therapy, even subtle changes, right? So you've heard of RECIST criteria in using CT-based response evaluation in solid tumors. Well, there's the PET version of that, the so-called PET response criteria in solid tumors, PERSIST, which can be very powerful. So how does this happen? Basically, in this phenomena, what you have is a proton giving rise to a neutron plus a positron. Now, this is a neutrino, and it doesn't really matter. for all practical purposes, but these two matter. And so, for example, if you have oxygen 15, that gives rise to nitrogen 15 with a positron. And that positron is emitted with a range of energies. And then after that positron is emitted, it might travel a little bit. So here's an example. You got an unstable parent, gives rise to a daughter, and in that phenomena releases a positron. A positron is a positive electron, same weight. It's an anti-electron, same weight, it's just positive. And then it travels a little bit, often less than 1 millimeter. It depends on the radiopharmaceutical. Some radiopharmaceuticals give you more energetic positrons, some give you less energetic positrons. So for example, in F18, this number is actually less than 1 millimeter. So after traveling a little bit, then it combines with an electron. The two of them annihilate and give rise to 2 photons. So it's a classic example of E equals mc squared. The original rest mass of the electron positron is obliterated and you only get photons left. And these two anti-parallel 500 keV photons are generated. Now, notice the energy is quite high. It's not like 140 keV for SPECT. So we got an issues. PET, this is why PET is so expensive, because these are highly energetic photons. So you got to build the machinery to detect such high energy photons. So that's what makes PET expensive. But it's extremely powerful because you get 2 photons, not 1. That doesn't mean just that the sensitivity is just times 2. No, it means sensitivity is like times 100. You may say, well, why on earth is that? So hold on, I'll tell you why in a second. Hold on to that thought. So again, just showing the same thing. You got positron annihilating, and you get 2 anti-parallel photons. Now, if you have a coincidence detection system that says, hey, at almost the same time, because these two are detected here at almost the same time. Sure, this one is a little bit closer to here, so this one gets here a little bit faster than that one. But roughly they're arriving at similar times. If I have a coincidence detection system says, hey, I got something here, I got something here, I'm going to draw a line of response. It must have come from somewhere along this line. Okay. Showing the exact same thing. Again, you've got, let's say, accumulation in a malignant cell. You've got 2 detectors that are detecting the 2 photons coming from it at almost the same time through a coincidence circuitry. You know that, you draw a line of response. Okay. And then from that, you can end up reconstructing. You don't know where along the line of response it came from, but that's okay because you're going to be collecting data from all angles. And in tomographic imaging, if you're collecting from all angles, it turns out mathematically you can invert the problem and get the original distributions. But still, hold on to the thought. Why is it that PET can be almost like even 100 times more sensitive than SPECT? Why is that? Hold on to that thought. So here are examples of radio tracers or radiopharmaceuticals used in CT. Again, you could label with C11, for example, nitrogen 13, oxygen 15, fluorine 18. These are some popular examples, but by no means limited to these. Fluorodeoxyglucose we already talked about in many different applications, but there's other ones too, right? So you could be studying. Sky's the limit because there's multiple different isotopes you can use, and then you could tag many different molecules with these, and therefore you're looking at many different physiological processes that you could be looking at. Examples of 6 radionuclides used in PET with their half-life. So again, F18 is very popular, under 2-hour half-life. Gallium-68 is popular also. And here you have the sort of positron range. You see that the positron ranges typically are less than 1 millimeter. A couple of examples where it's like quite more than, actually one example where it's quite more than 1 millimeter, because rubidium is highly energetic, gives rise to highly energetic positron. So the image might be somewhat more degraded. But again, fluorine 18, we're looking at sub-millimeter positron range. And the PET isotopes can be produced based on cyclotrons or generators, and there's the different economic models. For example, there's a debate about what works in each country and continent based on their business and economic models, right? So fluorine 18 versus gallium 68. There's different ways to produce these. we're now at a point where we can try to understand why sensitivity of PET is so great and so fantastic. So we said this before, if you're doing single photon imaging and you don't use any collimators, you don't know where these images came from, so you cannot visualize. So that's why we inserted physical collimators, which we talked about last time in gamma imaging, to restrain events that are coming in so that they're only coming at this angle. Otherwise, we don't know where they come from, which line of response they come from, and the reconstruction becomes near impossible. But when you insert a collimator, guess what you're doing? You're killing a lot of events. You want to understand which direction they came from, and in the process, you kill a lot of events. Turns out in PET, you don't have to insert physical collimators. Why? Because you have digital collimation. If you got two photons that are being generated, you don't need a collimator to be inserted here to kill events that are not coming at a certain angle. You have coincidence, and this says, hey, I just got something. This one says, hey, I just got something. We're at the same time, almost the same time. So let's draw a line of response here. So this one, you don't need a collimator to restrict what comes to it. You could have an event come to it at this angle or this angle. As long as there's a pair on the other side that says, hey, I just got something with you, and you can draw that line of response, you can measure that. So you're killing much less events. That's why the sensitivity can be something like 2, even 3 orders of magnitude better. So what a coincidence, right? So a coincidence event is assigned to a line of response, drawing a line, joining the 2 relevant detectors. And so there is no need for a physical collimation. This is electronic collimation. And that has 2 major advantages. Improved sensitivity, which I just told you, but it also allows you to get a more uniformity along the point spread function. You might recall that we mentioned last time that as you get closer to the collimators in a gamma camera, as you get closer, the resolution gets better. And as you're farther away, the resolution is worse. That's why when we image patients, we don't like to go in circular orbits. We like to bring them into, orbits that are closer, for example, to the chest of the patient. So the orbits may be non-circular, because we want to get as close as possible. But in PET, because you've got a detector here and a detector here, it's not just one-sided, it's 2-sided, one here and one here. Turns out that whether you're here or here or here or here, the resolution doesn't change much. Because again, you've got detectors on both sides, not just on one side. So increased sensitivity, right? And reduces this dependence of resolution on distance. Okay. So, but the challenge, and this is why PET is expensive, is the high energy 511 kV gamma rays. So how do we deal with that? So we need scintillators. We are obviously using scintillators for gamma too, but you need different kinds of scintillators for PET than for SPECT. So we talked about scintillators before, and or at least we referred to it, but the concept is that when you have an incoming gamma ray, it loses its energy in the scintillator. So gamma ray comes in, scintillator, loses energy, actually creates some kind of molecular excitation. And then when the scintillator, which is excited, comes back to its normal state, it glows and produces like actually visible light. And this visible light enters the photomultiplying tube, and then it amplifies it to give an electric signal. So again, high energy gamma ray coming in, the scintillator absorbs them, itself gets excited and then comes back to its own normal state, emits some visible light, much lower energies than here, but lots and lots of them. They enter here, and then through this PMT multiplication phenomenon, which we talked about before, you end up getting a strong current that you can measure, telling you what was the original energy that you detected here, because the more energetic that this is, the more scintillation light you get. So a large number of different scintillation crystals exist, and they have a number of properties. Again, we talked about this density, atomic number, light output, decay time, certain properties. But at the end of the day, if you want to absorb, if you want to stop highly energetic gamma rays, you got to have high density and high Z or high Z to stop it. But you don't want to just stop it. You also want to have a good scintillator, right? I could design something that is extremely dense that stops light, but you got to also scintillate. It has to be a good scintillator too. So inorganic scintillation crystals meet this requirement, having high stopping power, high densities, allowing you to do that. So here's a table, right? And sodium iodide, as is used in gamma imaging, meaning single photon imaging, for example, planar imaging and SPECT, you see it's less dense. And as people started thinking about PET and the highly energetic 511 kV instead of the 140 or lower energies, people are trying to use sodium iodide for PET, but it was not doing a good job. So people designed denser materials. Okay, so BGO, GSO, LSO. BGO and LSO you'll keep hearing, and they have very good properties. The stopping power is quite better than sodium iodide. Conversion efficiency is very good for LSO compared to sodium. Sodium iodide is great for conversion, even though it doesn't stop as well. But once it stops, it yields very good light. LSO comes close, and resolution again for LSO, because it emits a lot of light, the resolution also, energy resolution comes close. And one of the cool things or important things is that the decay time with LSO is also small. It means that the scintillator almost has smaller dead time, like it doesn't get saturated as easily because the processing time, every event that it processes takes less time than the other one. So the community has really towards increasing usage of LSO or LYSO, which is similar to it, or BGO is still being used as well. So again, when something comes in, you get a pulse rise time, and you get an exponential. This is almost the processing time. Scintillator, something hits it, it gets excited, it starts to emit things, excited, and then all this processing is happening, and then it starts to an exponential decay time. So this is rise time, decay time. And so you want to have and these two are sort of correlated. So the faster this is the faster that is. So if you have fast rise time, that means you can really reduce the so-called random coincidences. We'll talk about that later. This allows you to also enable time of flight later. Just hold on to that thought. These two words are important: random coincidences and time of flight. We'll come back to that later. Faster decay time, as I just told you, gives you less dead time because there's less saturation. You're quickly getting over this processing time. So if a new event comes in here, you're able to process it. Whereas if this was taking forever, then a new event comes in, it doesn't have time to process it. Another important improvement, or besides improving crystals, was how we couple crystals to PMT. So last time we talked about Anger logic, right? By what Mr. Anger did. Similar here, it's the same as Anger logic, really. It's very analogous to that. That you build a block of detectors and you couple it not one-on-one, but you couple a whole set of detectors with just a few PMTs, and through Anger logic, it figures out where it came from. Because even though the resolution of these two looks terrible, but if you got an event here versus here, this one here is gonna deposit almost all of its scintillation light here, whereas if this guy is here, most of it goes here, but some of it goes here, and this guy is here, half of it goes here, and half of it goes here. By averaging between how much signal this is getting versus that is getting, you can actually calculate where along this you're detecting, and that's X, and then you could do it similarly for Y. This is how visually it looks, and again, visually is how it looks. Let's say an 8x8 coupled to a 2x2 set of PMTs, and again, depending on where you are on the X and the Y, the amount of signal you deposit in these four will be proportionally or somewhat, changed, and then you can figure it out through Anger logic. Different scanner designs have been considered. This is a very popular one, just a circular design, but you've also had these ones, right? And you've also had partial ring designs, right? But these are the most popular ones. They're fully covering the field of view, but people are exploring the idea of partial ring PET scanners, especially with artificial intelligence. Idea that you can probably do better reconstruction, fill in the gaps, etc. Okay, so so what are some of the important technical advancements besides what we just mentioned? What did we just mention? We talked about the idea of using good and better scintillators. We talked about the idea of moving beyond one-to-one coupling, and instead of one crystal being mapped to one PMT. This would make PET scans super expensive because for every crystal, you're going to need one PMT. Whereas here, for every 64, you need 4 of them. For every 64 in this design, you need only 4 PMTs. So you could actually create very good high resolution PET with only fewer PMTs, so making it not so expensive. But besides that, what else have been some of the developments? So I'm going to talk about some of the key developments in the world of PET. Time of flight PET, I promise you I'll talk about it. So-called 2D versus 3D PET data acquisition, not image acquisition. Images are always 3D. If you're doing tomography, your images are 3D. No, but acquisition itself. Multimodality, meaning PET CT or PET MR, and longer axial field of view imaging. So what is time of flight PET? Remember how I kept telling you, if you got an event here, this one technically gets here a little bit faster than that one? Well, can we measure that? Can we measure how much faster this one gets here than that? Because if you can measure how much faster this gets here than that, we can actually know where along the line of response the event came from. Because nowadays, normally, not nowadays, like in the original non-time of flight, this is what we have. We don't know where it came from, and so we would back project the entire thing. But because you're doing image reconstruction and you're collecting from all angles, you can figure it out. But what if you didn't have to back project this entire thing? Remember, you're having noise in your detectors. What if I don't back project this entire noise? And if I sort of have a feeling that it must be somewhere here because I got a signal here a little bit faster than a signal here. And that actually ends up reducing noise, as you can sort of see here. Now, if you had really, really, really good timing, you don't even have to do image reconstruction anymore. You just know exactly where this event came from, like here. But we don't have that kind of a good timing right now. So this is a conventional PET. You don't know where it came from. You would back project everything, do filtering, do whatever, iterative recon. You'll get it right. But at least this is how you back project it. But if your time of flight or the timing resolution in your coincidence becomes better and better, you're back projecting smaller and smaller segments. So it turns out, because you're back projecting less noise across smaller segments, you're going to get less noisy images. But if in the future, I mean, this is a projection of the past, and right now, we're talking, some clinical scanners that we're having are actually around 200 picoseconds actually. So this was a good prediction back then that was made in 2016. But if this trend continues, perhaps in the future, we might even reach this place, or maybe not. This may curve off like that. But if we go below a certain resolution, we might reach 2 millimeter resolution, which means we don't even have to do image reconstruction. We'll know within 2 millimeters if where the event came from. But we're not there yet, so we still have to do reconstruction. We still have to do back projections and stuff, but at least we're getting less and less noise. So existing time of flight does not improve resolution directly, but it reduces propagation of noise, therefore you get less noisy images, and allows your iterative recon algorithms actually to converge faster. So for a similar number of iterations, one arrives at a higher contrast image because it's converging faster without noise amplification, because it's reducing propagation of noise. So time of flight is great. So the scanners nowadays have it. This is an example of a non-time of flight image. This is the time of flight. If you look carefully, you'll see that contrast might be improved in some places, but look at this particularly. The contrast here is around 2, whereas here is 3. You start seeing some things at least more clearly. What's the other technology? Originally, in PET, the saying, you can't handle the truth. It's almost like the signal was just too much to handle. So people would insert some kind of septa, kind of like only between the axial rings, not within a plane, but only between the rings. Actually, they would insert septa, so they would just process. So they wouldn't have to process so much signal coming at oblique angles. So this is what people used to do, 2D PET acquisition, by inserting septa. But then people thought, well, why not get rid of it? So what? I mean, okay, we get more signal. Sure, more signal might mean that you're going to need greater storage and computational demand, but we'll deal with it. You may get more scattering, more random coincidences. I still have to tell you what random coincidences are. But okay, we'll handle it. But we do get much, much improved sensitivity because we're not killing these events. So in the same spirit that going from SPECT to PET, there's an increase in sensitivity, Same thing. Let's remove the septa and we go from 2D PET acquisition to 3D PET acquisition, and with improved, image reconstruction, improved electronics to handle this increased signal that's coming. That switch was made. So again, going from 2D PET acquisition with septa between the axial planes, the patient would be lying like this, to something like this, improved sensitivity. So again, images got better. Another thing is that people do whole body PET imaging, right? So this is very popular and commonly used and prevalently used in PET imaging. You can do, because the sensitivity is so good, you can do a whole body imaging. Now, sometimes whole body means true whole body. Sometimes it just means, from here to here, for example. Okay, so it depends on the protocol, but it means multiple PETs. And the other thing is that we do multimodality imaging. As I mentioned to you, adding CT to SPECT or to PET allows you to measure how much attenuation is happening, but it also allows you the clinicians and the physicians to look at the images in fused mode. So again, CT can be used for better visualization. And when you're doing a single scanner combined PET CT, there's less shift and drift in the body. If you have some PET scanner here, some CT scanner here, while the organs move, etc., but it's on the same bed, you're just translating the bed. So you get better registration. Again, CT being used for attenuation correction. People used to use transmission sources, but that would add like an extra something like 20 minutes. But with CT, that's only a few seconds. So that's why, when this concept was introduced in the late 90s, people implemented in year 2000 the first clinical scanners that went from PET only to PET CT in the span of only 3 years. The market share of PET CT went from 0% to almost 100%. It was a revolutionary thing. PET only pretty much became PET CT. Okay, and so PET CT-based attenuation correction can reduce this duration from 18 minutes of these slow movements of transmission sources to only a few seconds, but it can introduce certain artifacts. For example, CT might be sensitive to metal implants, contrast media, but then there are solutions, workarounds around it. So I like this saying, structure without function is a corpse, and function without structure is a ghost. So PET CT allows you to do both. PET MR is also has been definitely a trend. There's a lot of excitement around it. When it started to show up, you could do sequential PET MR, kind of like PET CT, or you could even do simultaneous PET MR. They had to redesign the scanners because the PMTs, when you have photomultiplying tubes, you have a lot of magnetic field. It just messes things up. So they move towards solid state, solutions, semiconductor solutions. So yeah, this is what I just told you. So people consider semiconductor alternatives like avalanche photodiodes, APDs, or silicon photomultipliers. And these things were so good because they're more compact that even though people wanted them for PET MR, so they're not sensitive to magnetic fields, but they're so good that people are not even switching PET CT scanners to these kind of alternative semiconductor alternatives. And we sort of talked about last time about some advantages of semiconductor approaches to detection. But attenuation correction in MR is complicated because the MR signal is governed by proton density and relaxation mechanisms, as you know. And it doesn't directly correlate with tissue density, unlike CT. CT, it's about tissue density. It's about electrons. Okay, so there's a bit of a mismatch between attenuation for PET and MR, and therefore, what's happening here is that people have used other techniques like segmentation-based method, AI, or template-based methods, AI, to do this. But it's moving forward. The question really is PET MR worth it? Because it's much more expensive than PET CT. It's an amazing tool for research. Clinically, people have been looking for some applications for it. So it's continues to be an area of exploration and interest, but majority of scanners in the field nowadays are PET CT, not PET MR. And this is a new exciting development in the field where the axial field of view of a PET scanner, which used to be only like 10, 15, 20 centimeters because it's already so expensive. And then you would have to shift the beds, multiple bed positions to do whole body imaging. There's, some explorations came initiated by fantastic colleagues at UC Davis and then UC Penn and in Europe, etc., where they were like, well, why not just build a much bigger scanner? Now, you can imagine this is going to be monumentally expensive compared to that, right? But they took a risk and they activated the imagination of the community. For example, in this design where they went from, let's say, a field of view of 15 to like 2 meters, you could get a factor of almost 40 increase in sensitivity. So you could get much improved image quality. Or think of it this way, you could reduce the, if the sensitivity is 40 times more, you could reduce the imaging times to even less than 1 minute per patient. You could even think about doing breath hold PET. It's like, hold your breath, done. Well, not that fast, but Or you could significantly reduce injected doses to patients, pediatric, or you could even scan, you could do dynamic whole body because this patient is being covered across his or her body. And then what you're having is that you could observe the dynamics of the radiopharmaceuticals. So a lot of exciting possibilities. Or you could even image the patients many hours after injection. Like this is an example of a patient being imaged 10 hours after injection, and yet you're getting cool images. So it's pretty outstanding results. Here's an example of the kind of things we couldn't even imagine doing. Dynamic whole body imaging. Look at these times. Each reconstruction at the beginning is after every second. 1 second of acquisition gives you enough data to do image reconstruction. Watch. See that? Something's been injected. The radiopharmaceutical is being taken up. The heart is distributing it across the body. Now the image intervals are starting to become a little bit larger, maybe every few seconds. Then it's going to switch to every 10 seconds, maybe every minute. You sort of see these images. So providing just amazing images. So again, we're going from maybe here, which is what used to be, to here, and things in between, right? So for example, you could have a long axial field of view PET scan that's 1 meter long, right? So what are some of the data corrections that we can do in PET image? And can we achieve quantitative PET imaging? So, yeah, the answer is of course we can, but how do we do it? First of all, what are some of the things that degrade that the quality and the quantitative accuracy of PET? So we know. Then I tell you how we tackle them. So what are those key things, and how can we compensate for them? So I think mention something like 8 different things here. So attenuation is a big thing in both PET and SPECT. A signal originally intended to be detected in some detector may not be detected, either because it got absorbed, like in the photoelectric effect, or which is not really common in PET because the energies are so much higher, or it could be scattered away. When something's scattered away, it means it's not detected where it was meant to be detected. So for that original line of response, it's an attenuation. But then if it gets scattered away and gets detected somewhere else, that new place is receiving more stuff than it meant to, at least from that, for that particular point. It was not intended to be there, but it ended up being there. Random events, we'll talk about that. Dead time, sort of alluded to it. Variations in sensitivity of or pair sensitivities, decay, resolution degradation issues, like, you enter a crystal, but then you're detected in a nearby crystal. Things like positron range, we sort of talked about that. Photon collimator, I'll talk to you about it. Patient movements. So these are some things that degrade quality and quantitative accuracy of PET images. How do we tackle them? So let's talk about what a true coincidence actually is. A true coincidence is a cleanup event, right? So it's basically when the 2 anti-parallel gamma rays are detected, they're just being good, okay? Nothing's happening to them, you're just receiving them. And that's it, you draw a line of response. Yeah, and neither has undergone any interactions prior to being detected, and nothing else is being, this is it. These are the only 2 things that are being detected right now. Simple and easy. So let's talk about these 8 things. So attenuation. What is attenuation? Attenuation is the largest degrading contribution in PET. The good news is it's easy to actually correct for it in PET. Just hold on a sec. It happens when one of the annihilation photons is not detected. For example, it could be absorbed like photoelectric effect, but that's not likely at all in 511 kV. It's more likely at 140 kV, for example, for technetium imaging. Or it could be scattered out of the field of view. The 2 photons along a single line of response, consider them. The probability that a coincidence will be detected, meaning both will survive, depends on the path length only and not the relative position. Look at this here. You got an event here, it gives you 2 gamma rays. The probability that neither of these 2 is attenuated, and therefore both of them make it, turns out to be, you can look at some math, but it doesn't matter where the source is. It only depends on the line of response, the length of this length. It doesn't matter if this point is here or here or here or here. That's unlike SPECT. In SPECT, if you're here, because you're only giving 1 gamma ray, not the other second one, whether you're here, you're attenuated less than if you were here, because if you were here, you would have to go through a longer distance. But here, because you've got two photons, both of them have to make it. So it doesn't matter where the original source is in this line of response. So this actually allows you to do a straightforward calculation. And this is why people used to think PET is quantitative, but SPECT is not, because they didn't know how to deal with this in SPECT. But turns out in SPECT too, you can do it. It's more complicated than PET, but it can be done. So attenuation correction, you could, again, use transmission rods, or you could use CT to measure how much signal is being attenuated. And once you measure that, you can apply that to the reconstruction using different ways, like pre-correction of data or in the reconstruction step itself, and go from an image like this that has this dip in the middle because so much is being attenuated to something like this. What about scattering? Scattering is this. When you've got an event like this, one of them make it fine, but the second event, before it gets to detector B, it gets scattered, and unfortunately it's detected here. So you think now these 2 photons received it. You don't think they did receive it. You think that the original line of response you draw is this, and you think it must have come from somewhere along here. So you've been led by the scattering, by the Compton, misled by the Compton scattering. And again, because the direction is changed, you're going to be assigned to the wrong line of response. And even a small 30-degree scatter at the center of a typical scanner can misposition the event by 10 centimeters. So it's really messed up, actually. And in 2D mode, scattering used to be only 15% of the events. In 3D data acquisition mode, it's like 40 to 50% of events are scattered. So massive. So people used to say scatter is the enemy. So you got to deal with scattering. But there are very good techniques. It's challenging, but it's been tackled. It's challenging because to estimate scatter, you need to know the reconstruction, but to do the reconstruction, you need to know the scatter. But then you can do iterative methods, for example, or other techniques. There's a very popular model-based scatter correction approach that uses the attenuation map that you measure using CT, along with the emission data, a model of the scanner, and modeling of the phenomena of scattering, the so-called Klein-Machina formula, to figure it out. So again, you've got Compton scattering happening. There are formulas about the Klein-Machina formula sort of gives you estimates of different cross sections of photons. For example, if you're coming along this direction, right, and you've got a deviation here, this angle, what is the chance of getting this deviation versus that deviation versus that deviation? So, for example, for different energies, 0-degree deviation, this is a likelihood, relative likelihood. You can sort of see 0 is here, 180 is here, and things in between are like that. But you can calculate those and build those in your scattering calculations. Detection of random events. So what are random events? So look at these two, just hang in there with me. Look at these 2 events. These are 2 separate events, have nothing to do with each other. But by bad luck, they took place at the same time, almost the same time. and by another bad luck, one of their events was lost, let's say due to attenuation. It never made it to the detector, but the other one did. So one event from this, one gamma ray from this event, and one gamma ray from this event made it. These two others were lost. And by bad luck, they were at the same time. And suddenly the PET scan is confused. It's like, oh, I just got something here. I just got something here. It's all at the same time. It must be from the same event. So I'm going to draw a line of response here. It must have come from here, some event. But it was actually two events at two different places. So it's called a random event, random coincidence, when two photons not arising from the same annihilation are incident and detector within the coincidence timing window. And why is this other event lost? It could be due to attenuation, for example, that this event is lost. Okay, so for example, it got scattered away, so it got lost. But it might have also not ever even been meant for detection. Like if you got an event like this one will only give you that, whereas this one was never even meant to be detected. So you got a single event here, a single. And you could also just by bad luck, again, go through the detector not being detected. So you're going to get these single events, single hit, single hit. These two single hits are at the same time. I'm going to be confused in my system. And randoms happen in PET because you've got two photons. We've got a coincidence detection system. And so there are formulas. I won't go through this, but there are formulas to calculate based on some measurements that we make. What is the likelihood of measuring randoms? And you can actually build those into the reconstruction. There are ways to correct for randoms. It seems like a very complicated phenomena, but actually it's relatively easy to correct for it. It's almost like a background correction effect. Dead time. We talked about dead time a little bit. You can have two kinds of different types of dead time. One is parallelizable, one is non-parallelizable. Parallelizable sort of says, event one came in, I need some time to process it, let's say this much. If you come in the middle of my processing time, you've disrupted me, you've paralyzed me, and I'm going to penalize you because I don't know what to do now. Non-parallelizable, which is better, it says, okay, fine. You come in, I'm going to ignore you, but at least you won't paralyze me. I'll be done for the first event by this time. So some phenomena, and that time happens along the chain of imaging. You've got scintillators, right? You got PMTs, you got the electronics, you got the coincidence detection system. Some are parallelizable, some are non-parallelizable. But the point is that dead time is there. Okay, so dead time is there. And again, this is the incoming rate of events. As the number of events increases, the actual number of events you measure does not increase linearly because you cannot handle the truth. Okay, so there's more dead time. But if it's parallelizable, not only does it not go up linearly, at some point it starts to be truly paralyzed. Like if there's so much signal coming that I cannot process anything, I don't have time to process anything, I will not process anything. So in an extreme case, when you move here, down here, you might actually end up measuring nothing because it's just, I'm totally paralyzed. You're overwhelming me. I cannot even process, a few events here. There's some formulas for it, but that's the essence of it. Parallelizable is worse than non-parallelizable. And again, in nuclear medicine, we have a combination of parallelizable, like in scintillation detectors, and non-parallelizable, like some electronics contributions. Depends which one is dominant, right? Or when we need to model multiple contributions, like hybrid modeling, which one is, So for example, I used to work on a scanner. In that scanner, the key parallelization was, the key dead time effect was because of the coincidence circuit. It just couldn't handle events. And detectors came second. So this was a bottleneck. If you reach a certain amount of counts, let's say 30 million, singles per second, the coincidence detection just would give you artifacts. So it depends. So let me ask you all a question here. Besides radiation safety, what two phenomena limit injection of too much radioactivity into patients? In other words, let's say radiation safety was not an issue. We could inject our patients how much ever we wanted. Besides this ethical and radiation safety issues, what are some two things down here that tell you, you know what? No, you really should not be injecting too much. Attenuation and scatter, scatter and dead time, attenuation and dead time, randoms and dead time. What does everybody think? Any suggestions? Can you help me narrow it down? Anybody? So dead time is one of them, because I just said it. If for example, oh, we got somebody saying something. Okay. Somebody saying not sure. That's good. That's good to hear from you. So yeah, dead time is one, because again, if you inject too much, especially if you have a paralyzable system, right? And we always have paralyzable somewhere. Then it paralyzes, it gets paralyzed. So dead time is one. The other one is randoms. Why? Because remember, randoms depends on two events being sort of arriving here. You have two events, one here and one here. And if you're doubling or tripling the injected dose, you're going to get double or triple the number of singles, but then the number of randoms depends on singles here and singles there. So it's almost quadratic. It depends quadratically. The rate of randoms increases roughly with the square of the activity. So if you double the injected radioactivity, you might get 4 times randoms. So at some point, it starts to become terrible. So we cannot inject too much besides radiation safety and ethical issues. We cannot inject too much because of we're going to saturate the system through dead time, and we're going to get a lot of randoms. Okay. Variations in detector pair sensitivities is the 5th topic to talk about. We have several thousand detectors in PET, each requiring, each of these pairs. They're individually, they have their own issues, and then they're paired together, like there's geometric sensitivity between different pairs. Since a photon can enter a detector from different angles, there's angle-dependent sensitivity. It's something we don't have in SPECT, but in PET we have it, because again, we don't have physical collimators. A detector, events can come at it at different angles. So it would have different geometric sensitivities. If I come this angle, it might be less sensitive to me than if I come this angle. So you got a model for all of those. And the process to compensate for this phenomenon is called normalization. I won't go through details at all, but essentially you could have a rotating rod source, for example, that you put in there. You measure, how things are being detected, in a simple, original way. You would measure all possible, you would collect all possible detector pair measurements, and you just normalize. There are other ways to do this in a more rapid way. But the point is that, yeah, you can measure. But at the end of the day, you can measure this pair, how sensitive is it? This pair, how sensitive is it? So if I have uniform activity, I should be measuring the same thing. Or if I have uniform activity in this rotating rod, whether I go this way or that way or this way, it should give me the same activity, but it won't. And because of these different pair sensitivities, so you can correct for it. So examples where here's an image that has, actually, let's look at this image. Here's an image that has not been corrected for attenuation. See this dip in the middle. If you correct for attenuation, but don't correct for scattering, you get the opposite effect, which we sort of saw for SPECT. If you don't correct for normalization, you get something like this, which is a little bit patchy, I suppose. It's not as smooth as you can get it. And then if you do all of them, you get something like this, which turns out, I'm not showing profiles, but to be smoother, just better. Decay is the easiest one to correct for. It's the most straightforward correction in nuclear medicine. You can calculate how much within each frame. Let's say you got 5 minutes acquisition. You know how much within that frame the activity decayed. It's just a law of nature, you know it. And how much between frames, if you're doing dynamic imaging, or since the time I injected, how much has the radioactivity decay? It's very easy, very, very easy to do. Resolution degradation, all these different things that degrade the resolution of PET, you could actually model, but let's try to understand them first before we take a break. Resolution degradation can happen due to a number of reasons in PET. One is positron range. We already talked about that. The positrons need to travel a little bit before they get stopped and they combine with an electron to give you those anti-parallel gamma rays. There's also photon non-collinearity. This may actually shock you, but this thing happens. Technically, these two things may not be at exactly 180 degrees. Turns out because the positron, for example, may have a momentum, when it combines with an electron, there might be a little bit of a forward bend. Now, this is not a huge bend. This is an exaggerated drawing. We're looking at like less than half a degree deviation. But this less than half a degree deviation in large distances of like a 1 meter diameter scanner can give rise to something like 2 millimeters, 1 to 2 millimeter resolution degradation. There's also crystal blaring issues. If I'm entering a crystal at an angle, before it's successfully in stopping me, I may have penetrated to the nearby crystal. And so I may be detected here, not here, because I penetrated sideways, and it thinks I entered the crystal here, whereas I didn't. This gives rise to the so-called parallax effect as you move away from the center of the field of view, because you're going at the detectors at an angle. You get resolution degradation more here than in the center. But even if you're going at a straight angle or at a side angle, you may enter this detector, not penetrate, but you may actually be partially absorbed, but then scattered to nearby crystals and just get degraded. So, so I'm showing this because of the positron range that I showed you before. Again, the amount of positron range depends on the radionuclide. Again, fluorine-18, which is very popular, has very small positron range, which is good. Another way of showing the exact same thing, you've got original positron, travels a little bit, typically less than a millimeter, gets obliterated with an electron towards or annihilated, giving you the two gamma rays, but the gamma rays might be slightly bent, less than half a degree actually, but this deviation might be about 1 to 2 millimeters. And then it enters a crystal, it may penetrate through, that's one kind of problem, or make it you make it scatter in the crystal. Anyhow, you're going to get crystal blaring. You entered this crystal, but you may end up being detected here or here. Yeah, so we just talked about this. So you can actually, in the past, people used to say, well, that's just the way it is. Images are degraded because they are. But no, you can actually try to tackle these issues. So if you tackle these issues after reconstruction, people typically call that the partial volume effect. You model these phenomena. You try to sort of correct for them or account for them. But if you model these events within the image reconstruction, we typically call that resolution modeling. In the SPECT world, more commonly resolution recovery or PSF modeling, which the vendors are providing nowadays, giving you sharper images. Again, different vendors do it differently. You can model, for example, what's the likelihood if I enter a crystal at an angle, how I will blare, and you could model these blarings into your reconstruction, getting sharper images. So again, here's a typical acquisition where you see the parallax effect as you move away from the center of the field of view, because you can't handle those events entering crystals at an angle. But once you do resolution modeling, you get less parallax effect. Here's an example of a reconstruction without PSF modeling and with PSF modeling. You see, it looks sharper. It looks better. At least it looks better. Quantitatively, it can be better. Detection-wise, it can be better. It's not as obvious as time of flight. Time of flight, no question. Doing it is always better than not doing it. PSF modeling, it can improve performance, but you have to be cautious about it. In fact, sometimes you may get edge artifacts or overshoots. So here's an example where at the edges, you may get these edge artifacts when you do resolution modeling, or edge overshoots. So examples of images without resolution modeling, but when you do resolution or PSF modeling, you may get these edge artifacts which are not real. So you got to be careful about it. So for some brain imaging applications, I remember when I was at Hopkins, we would turn this off in the clinic. So again, I showed this before for SPECT. When you do no correction, then when you do attenuation, then you do scatter, and then maybe resolution modeling, the images change and tend to get better. So I have this review article. You may want to check it out. It's called PET versus SPECT. To my great surprise, it's been accepted by the community with lots and lots and lots of citations. I don't know why. It's probably because there's a nice comparison between the two modalities where it's almost like it's a face-off between PET and SPECT. And that comparison, the reason I wrote it that way was because by comparison, sometimes you learn about each modality better. So when you compare the two, you learn more about each of them. So some of the key points in this article were that some positron emitting isotopes can naturally occur, whereas and therefore can be readily incorporated in useful radiopharmaceuticals. That's not really physics, that's chemistry. But moving on to the physics, which is the core part of this article, attenuation in PET is not depth dependent and it's easy to correct for. We don't need a collimator, a physical collimator in PET. That's why we get a much better sensitivity by orders of magnitude. The blurring is no longer dependent on your distance to the detection system. But we do get random coincidences in PET, which we do not get in SPECT, which is one reason you cannot inject too much. We do get increased scatter fractions. So these are more complications, but the reconstructions tend to handle them well. And there are some limitations where, for example, in PET, we have positron range and non-collinearity. We don't even have that in SPECT, right? But again, you can model these in image reconstruction algorithms, for example, as an example, to the resolution model. So it's good to know all of these. Finally, patient motion. As spatial resolution improves in PET imaging, having gone from, order of centimeter to half a centimeter, now trying to get below half a centimeter on some PET scanners or small animal PET scanners, we're looking at 1 or 2 millimeter, 3 millimeter resolutions. Patient movements, become more significant because it's not just the resolution of the camera that matters, but a resolution of the movement of the patient. Like think of motion as almost like a blurring operation. So as you build these, great scanners, unless you deal with motion somehow, then you start being, as you make this number smaller and smaller, if this number doesn't get better, you're not going to have a good effective resolution. So there's different types of motion due to cardiac cycle, due to respiratory cycle, and other kinds of motion due to coughing, drifting, leg crossing, etc. Right? So we sort of talked about gating methods before, sort of, right? So the idea that you could do respiratory, you can measure the respiratory cycle and do gating and separate the signal into separate gates. You could use an actual hardware to look at the human breathing cycle, or you could do software data-driven approaches. But this is an active area of research. So those are 8 confounding issues in PET, and there's a solution to every one of them, and that's why PET images have become increasingly better. So the standard uptake value, SUV, is a term you'll keep hearing in the nuclear medicine world, especially in the PET world, but it's also increasingly used in the SPECT world. So there are limitations to visual assessment. It may not be optimal for looking at subtle changes like impartial response or small early changes before full treatment effect is complete. It's a bit subjective. And some clinical trials, I think consistent analysis is important, and inherently it's non-quantitative. That is not to think that this should replace visual assessment. I think it's more about sort of providing value and added value to the human decision maker. The human is central in this whole thing, and AI and quantitation all should be at the service of what we decide needs to be done. So quantification is important. It can add value, and if all the previously described corrections are made, the reconstructed image voxel intensity will be directly proportional to the radioactivity. So you know how much is better. It's kind of powerful, actually. By scanning a uniform cylindrical source of known activity, then you can use a calibration factor to change, voxel intensities to, the radioactivity, like kilobecquerels per ml, whatever the units of concentration used. So here's an example of a patient over time, background radioactivity, SUV mean, relative distributions. So SUV can give you certain numbers that allows you to track things. SUV is not concentration. It's like a normalized concentration with respect to, for example, some kind of background. You'll see it in a second. But it can be powerful in looking at treatment effectiveness. So you see how the values here from 9.3, 3-month post-treatment have gone to 2.1 and 1.8. So this is a definition. SUV is the measured concentration, which are the units I mentioned, like kilobecquerels per cc, for example, divided by the injected activity, which you inject into the patient, divided by some normalization factor, for example, the weight of the patient. So this is the weight of the patient. These almost have the same units. This is concentration, and this is how much you injected into the patient divided by the total volume or the total weight of the patient. Roughly, give or take, the kind of, this is almost like how much, if everything distributed uniformly throughout the human body, what kind of concentration would you get? And this is like, how much concentration did you get? So the SUV of 1, for example, could sort of mean that it's not elevated. So that thing could be body mass that you normalize to, lean body mass, etc. Sometimes when you normalize by the lean body mass, you may call it SUL. But again, the point is that SUV is the decay-corrected activity concentration divided by injected dose divided by, let's say, patient weight. So you can sort of see that, you know, if you think of 1 ml as having 1 gram, like for water, soft tissue, roughly speaking, an SUV of 1, you know, whether you're injecting 1 milli here into this or 1 milli here into this, sure, this is going to give you more concentration because this is smaller. But once you normalize by the injected dose and the patient, let's say, weight or size or volume, it's going to normalize out. And you're going to get an SUV of 1 in both of these images. Even though this is more concentrated, because you're normalizing by this, you're going to get an SUV of 1. SUV of 1 means like average of background uptake. If you, for example, here, make the volume smaller and make the injected radioactivity even higher, again, this is going to be very dense, very concentrated, but again, SUV is still going to be 1 because this is going to normalize it at the bottom because you're going to divide it by a higher number. So there are a number of factors that affect SUV. There are things we've got to do right, certain things that we can minimize with careful quality assurance or with consistent protocols, some over which we have some limited control, some over which we have no control. So things like clock synchronization. We got to know what is the exact time between when I measure my radioactivity and when I inject it into the patient, something like that, right? You got to enter the correct weight and height of the patients. You gotta quality of the injection has to be good. You got to make sure the entire injection enters the bloodstream, et cetera, et cetera. Okay, so certain things we can minimize, like proper stability of the dose measure calibrator to measure the injected dose, the scanner itself being stable, doing good QC, QA, which we sort of talked about last time. Things we can minimize with consistent protocols like patient preparation, right? If a patient is not fasting, that might really complicate things because the body might show certain metabolisms. That's because the patient is not fasting, not because there's elevated activity due to disease. Definition of the regions of interest, consistent definitions. Sometimes you have some control over patient motion. Playing and using consistent protocols and parameters can make a difference on the image noise. And there are certain things we just cannot control. Even if you have the same patient, everything else being perfect, but it's the same human showing up today versus tomorrow, there may be biological variability. And there's just nothing you can really do about that, even after controlling proper fasting, everything. So how you define the ROI matters. Are you going to measure the maximum pixel, maximum uptake? How are you going to draw the regions of interest? Or are you going to take this thing called ROI peak, where you make a sphere that's 1 cc, move it around the tumor to see where you get maximum uptake? Different ways to calculate SUV, for example. SUV max, yeah, it's the hottest pixel or voxel. But if you do SUV peak, where you take a 1 cc volume, move it around until it's maximized, it may show another part of the tumor. It may give you different values. And there's some variability associated with this, right? So if, same subject being scanned today versus tomorrow, some kind of a test retest, there's variability in the measurements. SUV max, whether you calculate SUV peak or average tumor uptake, there's variabilities in there. It's not going to be perfect. There's day-to-day variability. Part of it, again, is due to noise, due to the scanner, everything else. Part of it is due to biological variability. If you do some math, et cetera, you can show and prove, given the studies that have been out there. Look at this number, 28%, almost 30%. The 95% limit of repeatability is almost 30%. What does that mean? It means that if I image you today and you come back tomorrow and I image you again, test retest, there's a 95% confidence interval that these two are within 30% of each other. So if the change is more than 30%, it's highly likely that this is not due to biological and noise variability. This is due to real change in the patient, which means that treatment, for example, is working or not working. If you scan me today before treatment and sometime after treatment, and that changes more than 30%, that's very likely it's a real change. It's not due to biological day-to-day variations in the patient. It's a real change. So in fact, the PERSIST criteria use this number 30%. So they say if the change is, so let's talk about it. PERSIST stands for positron emission response criteria in solid tumors. My colleagues at Hopkins, when I was there, did this amazing work, and Dr. Martin Lodge was my outstanding colleague physicist, and Dr. Richard Wall and others were clinicians over there just leading this effort. Highly cited work. So they were sort of, first of all, saying that there's a threshold. They say measure the standard uptake value in the liver, and the tumor uptake has to be more than 1.5% of that mean plus some kind of variability in it. And then there's 4 criteria: complete metabolic response in therapy, partial response, stable disease, and progressive disease. And you see this number 30% keeps showing up. So for example, if you decline by more than 30%, or right, meaning if you or if the other way around, if that actually starts to increase by more than 30%. So 30% is this number that's arrived at by some mathematics and some statistical considerations. If it's more than 30% change, it's very likely it's a real change. There's other techniques beyond SUV. There's phylokinetic modeling, which really tries to look at better quantitation of physical phenomena, like for example, rate of metabolism. SUV is not the rate of metabolism. SUV is almost semi-quantitative. It's a measure of how much radioactivity, in a sense, is here. But how can we quantify the rate of metabolism? There are techniques to do that, but often they require dynamic imaging. There's a lot of interest and activity in this area. Moving beyond just measuring intensity, because SUV is a measure of intensity, but looking at volume of tumors. There's study after study showing that the volume of a tumor for certain cancers can be even more telling than the intensity of a tumor, right? So that's important. And also doing AI, artificial intelligence and radiomics, where you don't just look at uptake or volume, look at texture, heterogeneity, which might indicate things like hypoxia, proliferation, et cetera, et cetera. So there's a lot of interest in this area. So in summary, efforts to move beyond purely visual assessments are happening. SUV has been widely adopted for PET and increasingly for SPECT. There are different kinds of SUV measures: SUV max, average SUV, peak SUV. We need to understand variability of SUV and how to link it to response assessment and look at other metrics beyond SUV only, intensity only measures. So there are some artifacts in the world of PET that we have to be aware of. There's really 3. Their sources could be coming from the hardware, the acquisition, and the processing. It's important to have a good understanding of the acquisition and processing hardware used and the different processing steps involved. So for example, there's something arising from the coincidence detection being faulty, or the detector specifically failing, or the memory failing, or some kind of a processing hardware failing, right? So here's a coincidence detection. You've got a ring around the patient. Remember, in PET, we've got a stationary system. Because again, the beauty is you could collect from all angles. You don't have to rotate something around the patient with collimators. It's a stable system. And when an event is detected, like a pair of events, this is a line of response. You could use a so-called sinogram. In the sinogram, you say, what is the angle of this event? Let's say the angle is this number here, whatever that number is, let's say 30 degrees or whatever. And as you move up and down, the position of this changes with respect to the center, like the perpendicular distance. So this line would be here, but then more lines, if I change in this direction, would be here. So this is like, this is what we get. And then if you think of just one detector, how it pairs and combines with all of these, turns out in the sinogram domain, if you plot it, you're going to get this line. Because both the angle keeps changing, these are different angles, and the distance from the center keeps changing. But you get a line in the so-called sinogram domain. So if you suddenly see in your sinogram data, in your projection data, in your data, measured data, a line like that, it probably means there's a bad detector. If it's thicker, it might mean that it's not just a detector, but the entire block containing, let's say, an 8x8 set of detectors that's out. Or if it's even wider, it might be the whole controller controlling multiple blocks that is out. So those are some of the things you can identify. And if you have a few of these, sometimes a single one of these doesn't really show up in the image, but then as more add, you sort of get ripples. Right, so this is a diagonal line here. And if you have a lot of detectors with dropping, so in a system with a large number of detectors, drop out of a single detector is not going to show up really. But if you have multiple detectors missing a whole block, you're going to start seeing it. And there are ways to deal with this. So there are ways to like say, okay, I lost some data. Well, obviously I got to fix my scanner, but also maybe I can go back and process my data somehow to fill in these gaps or to ignore those gaps. Ignore them intelligently, not neglectfully. And if a PMT fails, multiple detector channels are messed up because remember a PMT. So here's a 8x8 block, a block of 8x8 crystals with 4 PMTs. If one of these PMTs fails, it's servicing a whole bunch of detectors. That's gonna confuse things. Okay, so again, you could say fan-like ripples, but it's going to be more pronounced than a single detector failure. And you get a wider diagonal band if a PMT fails. There's other issues that can appear in images. Patient moves. There is misregistration between PET and CT that messes up the attenuation. So here's an example where the patient has moved. And when you're doing attenuation correction, let's say you're using the CT, but then you're doing your PET reconstruction, they're misaligned, so the corrections you're doing might be totally off. So when you then plot the CT on top of the PET, you say, wow, what a big misregistration. That contributed to the attenuation correction. So you have to go back, align them better, and then do the reconstruction. Sometimes you may get some artifacts like this, and you may look at this, you would be like, what on earth is this? Right, so these set of streaks. And then you inspect it and nothing seems to have failed. But then you look at the image domain, you see this high intensity sine waves across the sinogram, which shows that there is an area in the field of view. This means that there is a point in the field of view that is going to be very high uptake. And guess what? When you zoom out of this image and you go out, there is a point right here. Okay? So this could have been the retention of activity at the site of injection, poorly flushed injection line, okay? And so how do you deal? Okay, so I just identified, how do we deal with this? Well, if you use techniques that sort of model noise, statistical noise better, you might be able to tackle it because some reconstruction algorithms, if you have very high uptake somewhere, they may get messed up. But increasingly, image reconstruction algorithms are able to handle this kind of an issue. Because at the end of the day, this is not really an artifact. It's just that there's super high radioactivity here, and the reconstruction is supposed to deal with that. And bad information is worse than no information. And so when you have this very issue here that we talked about, well, sure, you could do a reconstruction. There are, again, some reconstructions that might be able to handle this, but some won't. And if you cannot handle it well, then at least you can block it out. So you could put something here, block it out, and in a way assume as though there's a gap in the scanner, as though you have no data acquired there. Not that nothing was measured. No, you model the reconstruction saying there's a gap in my scanner here. I'm not going to model that space. You know. So you sort of remove that data. Something like that. I mean, essentially what you're really saying is that any detector, any lines of response passing through that super high area, I'm going to assume I have gaps in my scanner. This is not to be taken as a rule of thumb. These are just examples of how we would play with data and to fix issues. If there is breathing mismatch, remember we showed the brain, now there's a breathing mismatch. That was another movement. Here's another movement. For example, on the dome of the diaphragm or liver, you would see that, or at the lung base, you'd see that. Some respiration mismatches. And so sometimes this is because of breathing, right? So the CT was at a different phase than the PET, for example. High density metallic implants can generate streaking artifacts on CT. And then when you're doing attenuation correction for PET based on the CT, that really messes things up. You end up getting very high intensity for PET simply because it thought there's so much attenuation here that I'm going to have to overcompensate for it. Whereas this was really not an issue at all for the PET world. It's just that it's a metallic artifact that really messes up the CT image, but it's actually okay. The PET image would have handled it fine if this CT was not suggesting super high numbers. And so sometimes if you then turn off attenuation correction, you see that might go away and you're like, oh, that's the problem. Now, how to actually deal with metallic artifacts on CT, that's a whole different debate, but or different topic, but you know, typically these have been dealt with pretty well. Processing artifacts, you might have just entered the wrong processing parameters. You might have told it it's F18, whereas it was C11, or you might have told it, oh, you might have forgotten to turn attenuation correction on. You might have used the wrong reconstruction filter. So you're going to get the wrong image simply because you, as an operator, entered in the wrong number. So all these things can be hopefully tackled better. I just want to share a few slides about a sense of urgency that we need to have more PET scanners in Canada and in our province. This is a plot from 2017 showing the number of PET scanners per million people. Now, these numbers have increased right now. And in fact, in British Columbia, which used to be the lowest, this number has increased because we have about 5 million people in British Columbia. Now we have 5 scanners. So this number is now 1. We have 1 PET scanner per million. But that's not a great number. This number, I mean, this is 5 years ago. This is average Canada. So we're less than average in Canada. But even Canada, when you compare to south of the border, again, Canada, we've got about, again, this is data from a few years ago, about 1.4 PET scanners per million people. You go south of the border in the US, we're looking at almost 6 PET scanners per million people. You go literally to the state below us, Washington State, and you see the number of PET scanners. So I think there's a sense of urgency and importance that we need to have more number of units. I think definitely more are planned to be installed. But I think it's very, very important for us to know about this discrepancy. You look at Japan also, the numbers are very high of this order, actually. So let's move on to, unless there are any questions, I want to move on to nuclear medicine therapy. It's important to know that nuclear medicine is not just about diagnostics and imaging, it's about treatment too. And it is now, in the past 5 years, it has undergone, I would say, starting a decade ago, but now it's very heated up. It's undergone tremendously exciting transformative changes in nuclear medicine therapy. So there's different names So radiopharmaceutical therapy is a name, but it's also known as unsealed source radiotherapy or radioisotope radionuclide therapy, targeted radionuclide therapy, molecular radiotherapy, or molecular targeted radiopharmaceutical therapy. But the idea is you have a radioactive molecule, radiopharmaceutical, that contains radiation, localizes to a location, sits there, emits particles to kill its target. Got a tumor, for example, expressing, creating a certain protein. If you have a molecule that targets that protein and it is tagged by and labeled by a radioisotope that emits particles. So emitting gamma rays is for imaging, emitting particles is for therapy. If it emits particles, like electrons, for example, it can kill tumors, for example. So molecules, radiopharmaceuticals, that are labeled with radionuclides. So people have done antibodies, these larger molecules, but increasingly people are also excited about small molecules, peptides, and then you would radio label them with radionuclides. Again, they localize and they irradiate the malignant areas. So some special examples of radiopharmaceutical therapy, radioligand therapy is when you're targeting receptors as your target. So-called peptide receptor radionuclide therapy, targeting specific kinds of receptors activated by peptides, and radioimmunotherapy when using antibodies, monoclonal antibodies. Okay. Whereas here, typically, we're looking at for peptides, for example. So, external beam radiotherapy is the paradigm you're all very familiar with. But molecular radiotherapy is different. You're injecting into the patient, it is going, the body is distributing it to targets throughout the body that are expressing a certain protein, a certain target, a certain receptor, and it sits there for tens of hours, for days, and bombarding it with particles. So the ideal procedure for radiopharmaceutical therapy is when you have highly specific agents that concentrate in the target and nowhere else, no organs at risk. That's the ideal scenario. That's never the case. Diagnosis is confirmed by some kind of imaging. So you're not just treating, but you're seeing what you're treating. That's Theranostics. We can do that. We'll get there. Agent delivers therapy dose to target only with minimal effect on surrounding tissues, and target is destroyed and procedure verified. So again, we're looking at radionuclide radiopharmaceutical therapy. The question is, why do we even use radiation to treat cancer? Doesn't radiation cause cancer? Of course, you're going to have lectures on radiation, biophysics, etc. And you're going to learn about all these things. There's really two types of damage. There's deterministic damage, where severity of the effects depends on the dose. And there are thresholds. So above a certain threshold, it is deterministic that you're going to get increasing severity due to the dose, cataracts, etc. But stochastic is when there's a probability, not severity. More doesn't mean worse, but more means more likely that you, for example, you're going to get cancer. So the probability of these effects depends on the absorbed dose. So the higher the absorbed dose, the more likely that you're going to develop, for example, cancer. There's no threshold, it seems. I mean, there's a bit of a debate about this, right? Is there a threshold? But no known threshold, I should say. And the probability of having the effect is proportional to the dose absorbed. So induction of cancer. So again, you got deterministic effects. And this lecture is not to deal with these. So why are we using radiation? Cancer cells tend to divide quickly and grow out of control. Radiation therapy kills cancer cells that are dividing, but it also affects dividing cells of normal tissues. So the danger to normal tissues, the organs at risk, is important to consider to minimize side effects. So it's always about a balance between destroying the cancer cells and minimizing damage to the normal cells. And the risk of producing a secondary cancer is always there, and is an area of intense interest. But the time, and the time required for a carcinogenic effect to develop will be many years, and is very likely to exceed the patient's life expectancy. Of course, this is a very sort of almost actually not almost, definitely an oversimplified statement. This is an area of active interest. Depends who you're dealing with. With children, their bodies are more sensitive to radiation. They have a longer life ahead of them. They're smaller. So how much you inject, clearly you have to be super careful with in pediatric context. Therefore, the image gently campaign. But the point is that you can have you can try to look for the right balance, right? And the public sometimes does get overly worried about this, whereas, of course, these therapies, as I'll show you some results, can really it can be used as great, tools and weapons against cancer. So you have an isotope that localizes. It might emit a bunch of things, alphas, which are nuclei of the helium, betas, which are beta minus is an electron, beta plus is a positron, gamma rays, you could have Auger electrons. There's a whole bunch of aspects about how they distribute, excretion aspects, etc., etc. So dosimetry is how to balance the amount of radiation to tumors versus normal tissues, right? For example, in external beam radiation therapy, that's the norm. In our field, radiopharmaceutical therapy, we're pushing for the community to perform dosimetry, because some people say, well, let's just inject the same thing to everybody because it's so amazingly powerful, and it is amazingly powerful. I'll show you some results. But we believe strongly that dosimetry is the way of the future. It's the ethical way to go ahead to measure how much actually is being delivered to the tumors and to balance the treatment efficacy with normal organ toxicity. So you got a delivery of an isotope intravenously, for example, let's say. You've got a target organ, okay, and you've got a source organ. So this is just a measurement thing. So for example, just a second, you inject. Okay, there is accumulation in these two different things. And you ask a question. Let's say you ask a question. How much radiation is this organ getting from this organ? So that's named source target. Okay, so how much? I want to know how much dose I'm getting here from what I injected, which is how much it accumulates, but also from nearby organs when they emit light, for example, that passes through me as it comes through me. So in turn, those calculations are normally using certain equations and resources by the MERT committee, and standardized models have been developed in the past, and there's increasing movement towards personalization. Instead of a, standard man, it's towards personalization. You need knowledge of the internal isotope distribution. So you've got to image the patient after you injected radiotherapy to see how much ended up where. Or even once you inject, if that thing you've injected itself emits gamma rays, you could actually use a SPECT scanner, for example, to measure what's there. And there's a number of problems in calculations. Data is scarce. You may not have a lot of information. The kinetics might have changed. Organ distributions may not be homogeneous, and the standard man is only a partial solution. Here's the standard man, but there's a need to understand more. Like, here's a question: if there's an accumulation in the liver, how much dose is going to go to the kidney for the standard man? But you've got a whole range of people. So there's been movement towards personalization of models, so they could do those calculations not just on the standard man, but on men and women of different ages, for example, right? And different body types, right? Different phenotypes. So again, moving beyond really conventional geometrically defined phantoms to voxel-based definitions, to fitting smooth surfaces to them, really high quality anthropomorphic phantoms. So there's a lot of movement in this space. This is area of active research I'm just sharing with you, pediatric models that are being developed. Just showing you some examples. Even for pregnancy, you know, sometimes it happens that sometimes somebody comes to the clinic and only later they find out that they're pregnant, even though they thought they were not pregnant. Or if they had to be imaged anyways, then you do the calculations in the case of pregnancy, you know, how much is being delivered. So again, to a fetus, you can have radioactivity delivered directly, right? But also indirectly through the body, through the rest of the body of the mother, right? Whether the activity ends up in the fetus or ends up elsewhere, but then through radiation enters and impacts the fetus. Yeah, so therapy using radioisotopes. Let's talk about that. It's a question of, okay, when you, for example, when you discharge a patient, what are some radiation occupational hazard issues, right? For the technologists, for example. So I want to ask you a question here. A diagnostic radiopharmaceutical may be injected at a certain radioactivity, let's say 10 millicuries. A therapeutic pharmaceutical may also be injected at nearly the same activity. Is this true? So for example, when we do FDG PET, this is how much we might inject. Is it true that a therapeutic radiopharmaceutical may also be possibly injected at the same radiopharmaceutical dose? Or does it at the same injected radioactivity? Or does it have to be higher than this? Anybody, any thoughts on this? I think usually the typical response is no, it has to be much higher. But the answer is no, it doesn't, because it depends on the half-life. For example, if you've got something that is having, for example, if you've got something that has a long half-life, which therapeutic isotopes do, even though you're injecting the same, let's say 370 megabecquerels, it's there in the body for a long time because there's a large half-life. It's not like F18 where the half-life is only 2 hours, the physical half-life. Here, the physical half-life might be days. It's actually okay to inject the same radioactivity, but that radioactivity is there to stay for a long time. So the total accumulated dose will be much higher, which is what we need. So yes, it's possible that the injected radioactivity is only 370 megabecquerels, which is 10 millicuries, but because it's there for a long time, it can be therapeutic. So these are different examples of how some of these things are injected or taken up orally, for example. And so different uses, indications, just some examples, okay? Lutetium and yttrium-90 are, for example, two very sort of important applications that are being used increasingly. So yttrium-90 is here. I didn't mean the antibody. I meant just using yttrium-90 in different applications, actually here for spheres. So I would say these two are very hot topics, and we can talk about them here. So you see the half-lives of the order of days, right? And they're emitting beta negative, which means electrons. So that's what the killing mechanism is, or the particle has been released. And so there's a lot of interest in palliative and curative treatment phenomena. You could be emitting beta particles, Auger electrons, or alpha particles. Now, some of these also emit gamma rays, which would allow you to actually image what's going on, which is amazing. True Theranostics. Well, Theranostics means, I'll tell you in a second what Theranostics means, but if you have a radiopharmaceutical or a radionuclide that emits both particles for therapy and some light for imaging, then the same radionuclide is theranostic in itself. So again, iodine is something that's been used for decades, okay? But there are new ones that are taking people away by a lot of excitement. So I'm going to skip over some of these radiation safety issues, or just go over them very quickly. From a radiation safety perspective, there's typically not much exposure to the public. Okay. One aspect with some radionuclides is the safe handling of excreted and body fluids. With a number of other ones, there is some gamma rays or some so-called Bremsstrahl lung X-rays coming out of the body of the patients. So it's important to understand exposure of the public to these. So even though they're being treated by particles coming out, but there's some light, some gamma rays or X-rays coming out too. So we have to understand how much that is, how safe it is to be around those patients. But the beauty of these things is that you can also use them for imaging. So that allows you to do radiation dosimetry while the patient is being treated. Okay, so again, I'm not going to go over these in detail. So here's an example of using samarium for palliative care of bone pain, with bone metastases, right? And again, the particles could be alpha, beta, or Auger electrons. They have different ranges, different tissues. So beta particles have longer tissue range, whereas alpha is more localized. And Auger is even more localized. Examples of alpha, beta, and Auger, right? So again, lutetium is popular, yttrium-90 is popular, but people are really looking at things like actinium for alpha therapy, etc. So again, beta can go a larger distance, alpha can be more localized, even do double DNA break, and Auger is even more local. So again, also the beta itself depends, like you could have two different betas, like lutetium or yttrium-90 have different beta, maximum beta minus. Beta minus means electron energy ranges. When the electron comes from in a nuclear phenomenon, we call that beta, because it's not coming from the shells, outer shells, it's coming from the generated because of a nuclear phenomena. But anyhow, it's effectively the same thing. The source is different, but you see the range in tissue of lutetium on average, or the maximum, is higher than the yttrium-90. So what is theranostics? Combination of two words, therapeutic and diagnostic. It's a very important word and field of research. It's a combination of diagnostic tool that helps define the right therapeutic tool for a specific disease. So it's extremely natural in nuclear medicine. Why? Because you can use a radionuclide labeled agent to diagnose disease for imaging, and then use the same thing or closely related agent to treat those diseases, like radiopharmaceutical radioligand therapy. So here's an example where you've got a molecule. This molecule, if it's radio labeled with something that emits gamma rays, then you can do imaging. If it's radio labeled with something else that emits particles, you can do therapy. So the idea that you can treat what you see and then see what you treat. So first see it, make sure it's there, then treat it, and then see follow-up during the therapy or after therapy, what you actually did to it. So you could take a number of patients, pre-select using imaging which one of these express those proteins, put them on therapy, and then follow what happens to them. So theranostic radiopharmaceuticals could be a single radionuclide that has both imaging and therapy, like iodine-131 gives you both particles and gamma rays, lutetium, yttrium-90, or two different radionuclides. One is for imaging, let's say gallium-68 for PET, and one is for therapy, lutetium-177. Okay, you could do that too. Don't notice lutetium-177 also gives you light, so you could, even in itself, it's theranostic, but you could also use it as a pair, where this is only for therapy. You don't really measure the gamma rays coming off of it, but you pair it with a pre-therapy PET, for example. So iodine-131, there's beta minus, there's that is being emitted. There's also gamma rays being emitted. So you can visualize what you're doing. So this is a patient, 30 millicuries, you're seeing what you're doing. You're seeing the accumulation. Okay. And then you could also use pairs, like iodine-131 for therapy, but then you do iodine-123 as a theranostic pair, because it has a much smaller half-life. Instead of 8 days, it's only 13 hours. So you could use this for pre-therapy diagnostics, and then you could do the therapy. So radiation safety issues, again, issues of external radiation and contamination by excretion that you have to be careful about. So the excretion aspect, contamination of patient's environment, These are things that one has to do. There are protocols about it, and I'm not going to go through that, those details. Another example, which is quite interesting, is yttrium-90 radioembolization for liver cancer. This is kind of a cool area. It's kind of like brachytherapy too. It's micro brachytherapy, because in a sense, what you deliver gets lodged in the vessels. It's actually a kind of a mix between radiopharmaceutical therapy and brachytherapy. It's this hybrid entity, which is not easy to categorize. It's a category of its own. Basically, what you do is you have yttrium-90, which emits electrons, and then you put them in radioactive beads, and you deliver them directly to liver tumors via a catheter. And then so it goes, and the catheter tip here, and then they get lodged here in the vessels. They sit there for a long time, and they bombard the heck out of the tumors, right? So here's an example of the infusion, and different kinds of spheres or beads that can be used. Okay, typically it's an outpatient procedure. Liver is a primary site, well tolerated. Focusing on liver tumor. And minimizing impact to non-targeted issue, and patients can be further treated because you don't block the vessels of the liver. So the beads, the radioactive beads, flow directly into the liver tumor, and three things happen. One, you're destroying tumor cells from within the tumor, right? Because they're there radiating it. Secondly, it's a radioembolization. You're embolizing the arteries, right? And so you're suffocating the tumor in a sense, and you're helping destroy it. And third, which is kind of an interesting thing, it can actually result in liver hypertrophy. In normal tissue, it actually can result in growth. So the fraction, once you're done, you may have had a case where you may have had a kind of a liver that was non-resectable, but after therapy, the tumor has shrunk and the normal tissue has actually sort of undergone hypertrophy, and the ratio has become just right so that it is now resectable. Some images of CT, for example, before treatment here and after treatment. And yttrium-90, how can you image it? Well, it's a beta particle emitter. That's a particle for therapy, but it also it can also result in so-called bremsstrahlung phenomena. So first of all, from a radiation safety, if it's emitting beta, do you have to worry about radiation exposure? The answer is yes, because when you've got beta particles that are slowed down or by the tissue, they lose some of their energy through the so-called bremsstrahlung phenomenon. As it's curving through here, as the beta rays are being produced here, it is curving here, it creates bremsstrahlung photons, and this sort of can come out of the body. So that's the issue. So there's a radiation thing associated with that, but you can actually use those bremsstrahlung X-rays to do imaging. Actually, so you could actually use SPECT imaging to visualize those X-rays coming out, and so you could do SPECT imaging and visualize what's going on there using the right energy windows, etc. There was also discovery that there's a very minute amount of PET signal, meaning positrons, very, very small amount of positrons. It's not even shown here because it's so small compared to the 99.9999%. It's a very, very, very small amount that people discovered. The fraction of positrons is so small it's even hard to see it here. Okay, so for example, fluorine-18 emits, relatively speaking, 30,000 times more positrons. So at some point people thought, well, so what? But then, because again, remember, PET is more sensitive than SPECT, much more sensitive than SPECT because of the coincidence detection, the fact that you don't have physical collimators. People ended up showing that because you're injecting high doses here into the patient for therapy, there's sufficient positron emission that you can actually do PET imaging. So people started showing that to the great surprise of many people. I remember the hesitations we all had in those years. Remember, like, are you kidding me? Are you really going to be able to do PET imaging of yttrium-90? And guess what? Look at the images, yttrium-90 PET compared to Bremsstrahlung SPECT. Bremsstrahlung SPECT is not really quantitative because it's very difficult to model in a detailed way. There are some attempts in making it quantitative, but it's very tough. But yttrium-90 PET can be more quantitative. But anyhow, both are options for imaging. And so improved PET scanners, you can get better yttrium-90 images. So the significant new excitement, though, is, okay, so in the past, we were having, like, let's say, iodine-131 therapy for neuroendocrine tumors. But then something happened. Okay, so just to show you, before treatment, after treatment, that's great. But then people started really focusing on, using amino acid peptides, these small molecules that really target the receptors that are being expressed on cancer cells, like for neuroendocrine tumors, for example. And so DOTATOC or DOTATATE are examples that do that. And you can radiolabel with something like gallium-68 to do PET imaging, okay, which is here. And radiolabel with lutetium-177 for therapy. Notice how this image is so different than the conventional fluorine FDG PET scan. You see more things. There's the imaging side, but the therapy side is pretty amazing too. So you get very high focal uptake with sparing of organs at risk, relative sparing, and you can really do better. So first of all, imaging-wise, the PET is superb sensitivity-wise in detecting tumors. Compared to CT and SPECT using other kinds of things. So gallium-68, DOTATOC. But then again, you're targeting the somatostatin receptors. They're sitting there for days and bombarding the heck out of all these tumors that are spread through the body. So this is before, this is after. Right, so the paradigm is you identify which patients express those targets, put them on therapy, and monitor them. So again, the idea is you have a molecule that targets some kind of a protein that's being expressed. You have a chelator that encapsulates the kind of a radionuclide that emits the radiation, the beta radiation for killing, and also possibly a gamma emission for imaging. Okay, so you image it, you're killing the tumor as you're sitting and binding to the cells that are expressing that protein, but also you're emitting some light, single photon light, for example, from lutetium. And if you do SPECT imaging, because it's gamma imaging, it's not positron, so it doesn't allow you to do PET, but it allows you to do SPECT. You can actually measure how much dose you've delivered to the patient. So this is dosimetry. We should be doing dosimetry, and we're pushing the community so that we're doing at least some kind of dosimetry, so we know how much we're actually delivering. So here's a question, true or false. Gallium-68 DOTATOC and lutetium-177 DOTATOC are theranostic pairs, while lutetium-177 DOTATOC can be a theranostic agent on its own. The answer is that this is true. This is for PET imaging, gallium-68, this is for therapy, while at the same time, the lutetium-177, not only does it do therapy, but it also emits a single gamma ray, so you can use SPECT to image it. So on its own too, it is theranostics. There's a lot of excitement in prostate cancer. So the so-called PSA you've all heard of, as we measure from the blood, but the PSMA, prostate membrane antigen, is this protein that is expressed and overexpressed in prostate cancer, correlates with aggressiveness, and there have been molecules that have been designed to target it, right? And then if you radiolabel those molecules, here's an example that was designed by Dr. Martin Lodge and his lab at Johns Hopkins University, where I was in our division. And basically, you see, compared to like conventional bone scans and PET scans, this one is more sensitive, finds a lot more things. For example, it can find a lot more things. And that's the imaging side, but the therapy side too. So this is the pre-therapy PET scan. Many of these patients are unfortunately hopeless. Nothing's working. Hormone therapy is not working. Nothing's working. Of course, external radiotherapy will not work here. But then you put them on these doses and you inject them with these PSMA radiopharmaceutical therapy doses, and over time, as you're doing, these are SPECT images of lutetium-177. As lutetium-177 is bombarding these tumors, you see how over time, over multiple cycles, you see how the responses are mind-blowing. So there's a trial in Melbourne with 30 patients. These are the kind of, there was significant decline in PSA response in many patients. These are the kind of images you would get. 8 patients out of those 30 before with tumors all over the body and after, just miraculous responses. These are the PSA levels. See how much they've significantly changed. So there's a paradigm shift in treatment of metastatic castration-resistant metastatic prostate cancer patients. And so well tolerated by patients, some pain relief in all of them, well tolerated. There are some studies, for example, in Australia that really showed that when you compared radiopharmaceutical therapy with chemotherapy, significant improvements to PSA reduction, to progression-free survival, and to objective response rate based on RECIST criteria and CT. There's a quite a larger North American study, or actually North America and European study, vision trial that showed that overall survival. So this is comparing radiopharmaceutical therapy along with standard care alone, and it showed that the overall survival increases by 4 months, and that progression-free survival increases by 5 months. Now, note, these were not personalized. Same dose, almost the same dose was given to everybody, and that needs to change. But even without that, even though it's uniform dose, non-personalized, no dosimetry in a sense, you're getting these significant improvements. So it's been transformational. What the research community and what we're trying to push is to say, no, you got to also personalize these, and you might see more tremendous improvements. Those are beta therapies, meaning electrons, lutetium, yttrium-90, but you could also do alpha therapy towards double DNA strand break. There were some studies, anecdotal studies, showing that when lutetium does not work, alpha therapy might work beautifully. So there's a lot of research in this area, sort of mind-blowing, images that were shown. There's a lot of interest in this area. Perhaps a combination of alpha and beta therapy, beta for longer range, alpha for shorter range. Great things happening. So when it comes to applications of radiopharmaceuticals to nuclear medicine, imaging and therapy, sky's the limit. There's many radioisotopes, many of them that are out there. There's many, many molecules that can be designed for different targets. So molecular imaging and therapy. So radiopharmaceutical theranostics, okay, so that's on its own. There's just so much that can be done in this field of molecular imaging and therapy, right? There's so much that remains to be done. And radiopharmaceutical theranostics is a truly exciting frontier in nuclear medicine, and that's it.